Imagine a world of endless white silence, where the wind whispers secrets older than civilization, and each snowflake carries the memory of an ancient climate. Welcome to Antarctica, the frozen frontier at the bottom of our planet, where ice sheets cradle hidden lakes, mountain ranges lie buried beneath kilometers of frost, and life persists in the most unlikely corners. In the next hour, we'll journey beneath the surface of this silent continent to uncover the epic story written in its layers of ice and snow, from verdant forests of Gondwana to the hidden realms of subglacial lakes, and from the heroic exploits of early explorers to the delicate balance that determines Earth's future. So find a comfortable place, let the chill of the southern wind soothe your mind, and drift with us into the heart of the great white continent. Soft, powdery light, drifting in gentle swirls, falls across an endless expanse of ivory silence. This continent, the most remote and uninhabited on our planet, lies cradled at the bottom of the world. Imagine standing at the edge of a vast, wind-whispered plain where the horizons curve in perfect stillness. Beneath your boots, miles of ice lie compressed into ancient memory, pressed down by eons of winters and silenced by relentless cold. Here, the air itself feels different, crisp and crystalline, almost musical in its purity, as though each inhale were conducting a symphony of frozen time. Antarctica is a land both familiar and unknowable, its story written in layers of snow and ice that measure up to 3 kilometers thick in places. These layers are like pages of a cosmic chronicle, each one etched with traces of tiny air bubbles, dust grains from long eroded mountains, and hints of the atmosphere that once was. Scientists have drilled into the ice, pulling cylindrical cores that unlock tales from hundreds of thousands of years ago, revealing how Earth's climate has changed, warmed, and cooled in rhythmic cycles. In these cores, you find whispers of volcanic ash carried on southern airs, pollen from forests that once thrived when the ice sheet lay thin, and even microscopic fossils of creatures that lived in warmer seas. But before these pages were sealed under frost, Antarctica was a place of verdant life and temperate breezes. Roughly 180 million years ago, in the age of dinosaurs, this frozen continent belonged to a supercontinent called Gondwana. Towering conifers, ferns, and podocarps reached toward a sun that shone upon very different polar skies. Giant reptiles, both terrestrial and marine, roamed freely in environments that, to our eyes today, seem almost unimaginable. Lush riverbanks winding through emerald woodlands where now only cracking ice remains. Then came the slow, inexorable march of glaciation. Over immense spans of time, Earth's climate cooled. The southern seas grew chillier, ice began to form along the coasts, and glacial sheets advanced inward like silent armies, devouring everything in their path. The forests vanished, ancient river channels were swallowed, and the ice reclaimed the landscape with a patient, unwavering hand that continues to this day. Even now, each winter season fellowships with the continent's core, adding fresh snowfall and ice, only to have much of it swept away again in the summer as katabatic winds, those gravity-driven gusts, hurtle down from the plateau at hurricane speeds. Beneath that thick veneer of ice, however, lies a world as mysterious as the one above is austere. Subglacial lakes rest in hidden basins, such as the legendary Lake Vostok, sealed off from the surface for millions of years. Here, scientists suspect might exist microbial life forms that have survived in complete isolation, evolving independently from any influence of outside ecosystems. The pressure under the ice sheet keeps the water from freezing, warmed slightly by the Earth's geothermal heat, creating a dark, subterranean sea that could hold clues to life's adaptability and perhaps hint at what might dwell beneath the frozen surfaces of other worlds. Not far from these lakes, mountain ranges pierce upward, their peaks scraping against the ice's underbelly. The Gamburtsev subglacial mountains, hidden forever from sight until modern radar surveys revealed their grandeur, are comparable in scale to the European Alps. Erosion patterns cut into these rocks suggest rivers once ran wildly across the surface, carving valleys now buried beneath kilometers of snow. Volcanic activity, too, brews quietly beneath the ice, with subglacial eruptions believed to have fueled ancient ice streams, propelling them rapidly toward the sea in roaring surges. Along the edges where ice meets ocean, vast floating shelves extend outward with graceful dignity. The Ross Ice Shelf, larger than France, hovers above the waves like a colossal table, its edges precipitating brilliant blue icebergs that calve calmly into sleepy waters. These giant sculptures drift away on the Southern Ocean, their sculpted striations glowing in the low polar light before eventually melting into the current and raising sea levels across the globe by imperceptible millimeters. As darkness falls for 6 months of the year, the continent becomes a realm of long, star-splashed nights. Auroras shimmer overhead in curtains of green and violet, dancing across the sky in slow ease. Temperatures plummet to extremes that would freeze the soul, yet life persists in hardy lichens clinging to rocky outcrops, in seals and penguins that thrive on krill-rich seas, and in birds that soar above the ice, defying the void itself. Even microbes burrow into the ice, eking out existences in films of liquid water clinging to crystal surfaces. Their persistence is a testament to life's tenacity in the face of absolute adversity. And so, this remote wilderness, wrapped in blankets of snow and mystery, holds within its frozen heart secrets that echo with tales of ancient forests, extinct creatures, hidden lakes, and restless volcanoes. Each layer of ice is a verse in an epic poem written in chills and ancient winds, in pressure and patience, in the slow artistry of glaciation. It is a story that continues to unfold, with every snowfall and every calving iceberg, adding new stanzas to a narrative as profound and unending as the silence itself. A pale glow on the horizon heralded the first human forays into this frozen realm, when wooden ships, driven by curiosity and ambition, crept cautiously into pack ice. In 1823, expeditions sowed to Russian intrigue, British enterprise, and American enterprise claimed sightings of the continent's coastline nearly in unison, as if drawn by an unseen magnet. Thaddeus von Bellinghausen, aboard the Vostok, discovered icy fringes while mapping the southern seas. Aboard the Isabella, under John Davis's command, sealskin and ocean spray told tales of endurance, and American sealers, led by Nathaniel Palmer, were drawn southward by profit, only to find a savage beauty beyond their reckoning. These early navigators, battling roaring storms and skeletal icebergs, charted frozen capes and glacial mountains, naming them after patrons, ships, and loved ones left far above the polar circle. The age of wooden hulks gave way to steel hulls and steam, and with them came the true spirit of exploration. James Clark Ross and the HMS Erebus and Terror pushed deep into the Ross Sea, his funnels billowing smoke like ghostly phantoms through the ice. In January of 1841, Ross approached the Great Ice Barriera, seemingly infinite wall of ice, its azure underbelly glowing beneath the calved spires above. He named it the Victoria Barrier, but today we call it the Ross Ice Shelf, a colossal floating platform that supports the weight of history itself. His chaplain, gazing at towering peaks offshore, christened the volcanic volcanoes Mount Erebus and Mount Terror names that would echo in scientific annals and tragedy alike. Yet for decades, Antarctica remained a prize too costly and perilous to pursue beyond mapping its perimeter. Only in the late 19th century did a new wave of adventurers, poets at heart, yearn to stand upon its core. The Belgica expedition of 1897–99, under Adrien de Gerlache, endured an unplanned winter locked in ice, battling scurvy and deteriorating morale. But from that frozen cocoon emerged lessons on survival and camaraderie, recorded in journals that read like epic poems. Their ship's doctor, Frederick Cook, studied the behavior of penguins and collected botanical specimens, a reminder that life persisted defiantly at the margins. Soon followed the great heroes of the heroic age. In 1924, Robert Falcon Scott, aboard the Discovery, disproved the notion of an open polar sea, confirming that the ice stretched endlessly southward. His vivid accounts, suffused with poetic reflection, contrasted with the brutal environment that icily repaid every misstep. Roald Amundsen, foreseeing the demands of polar travel, trained his crew and sled dogs with Inuit techniques learned in the Arctic. His choice of supple huskies, high-fat pemmican, and meticulous planning laid the groundwork for success. But the greatest test of human will came in the race to the pole. Roaring engines and aluminum sledges might have offered speed, but it was painstaking discipline and respect for the ice that set Amundsen's party apart. On December 14, 1911, he planted the Norwegian flag at its southernmost point. A month later, Scott's party arrived, only to fall victim to bitter cold, physical exhaustion, and tragic miscalculations. Their diaries, found beside frozen tents, bear witness to the poignancy of dreams chased to the brink of oblivion, hunger, frostbite, and the knowledge that rescuers lay tantalizingly close, yet unreachable amid the vast whiteness. As word of these triumphs and tragedies spread, Antarctica's mystique only deepened. Governments and scientists recognized that this remote continent held keys to geological history and climatic patterns far beyond its icy borders. International cooperation began to form in the aftermath of World War I, culminating in agreements to share data, establish protocols, and respect the sanctity of the land. Yet all the while, beneath the ice, the hidden world continued its slow drift. Lakes remained undisturbed, mountains stayed cloaked, and the heart of the continent awaited further revelation. With the advent of airborne surveys and mechanized transport, the mid-20th century ushered in a new era of scientific conquest. Planes outfitted with magnetometers and ice-penetrating radar traced the outlines of subglacial mountain ranges, revealing peaks that rivaled the Alps in grandeur. The Gamburtsev Mountains, hidden for millennia beneath kilometers of ice, emerged on maps like a myth, their valleys carved by rivers that vanished long ago. Geologists probed rock samples from exposed Nunataks rocky islands, protruding through the ice sheet, unlocking records of plate tectonics and ancient climates that reshaped our understanding of Earth's history. The establishment of permanent research stations marked a turning point. In 1957, during the International Geophysical Year, nations rallied to construct huts of steel and aluminum in windswept basins and along frozen coasts. Soviet scientists settled at Vostok Station, drilling boreholes toward the hidden lake that would bear their name. The Americans built McMurdo and Amundsen, Scott's South Pole Station, where winter crews survived months of polar night in a world devoid of sunlight. Everyday tasks cleaning snow and repairing generators became rituals of survival as temperatures plunged below -80 degrees Celsius and isolation stretched into months. Science flourished in this white crucible. Meteorologists logged atmospheric conditions that influenced global weather patterns, while glaciologists measured the flow of massive ice streams that glided toward the sea like slow rivers of stone. Ice cores pulled from the plateau yielded snapshots of carbon dioxide levels and temperature fluctuations extending back 800 years, substantiating theories of greenhouse effects and climatic tipping points. Biologists studied krill blooms beneath the ice edge, discovering the keystone species that underpins the Antarctic ecosystem, tiny crustaceans, whose lives fuel whales, seals, and penguins in the nutrient-rich seas. Yet even amidst achievement, the continent remained fragile. The ozone hole, discovered in the 1980s, opened above Antarctica, warning the world of chemical harm that transcended politics. International treaties, most notably the Antarctic Treaty of 1950, safeguarded the land for peaceful, scientific purposes, banning military activity, mineral extraction, and nuclear tests. Visitor regulations and environmental protocols grew ever stricter, limiting tourist ships and research footprints so that the pristine snowscapes might retain their integrity. Beneath our feet and beneath the ice, however, the story continues in silence. Subglacial volcanoes, such as Mount Erebus and lesser-known geothermal hotspots, stir molten rock and warm basal ice, lubricating glaciers and potentially triggering sudden surges of movement. Subglacial lakes like Mercer and Whillans connect through networks of channels, sometimes draining and refilling in explosive bursts that reshape the ice sheet above. These hidden hydrological systems may influence the stability of Antarctic ice as the planet warms, carrying implications for sea level rise that ripple across the globe. On the surface, satellite constellations and autonomous drones now monitor crevasse formation, ice shelf thinning, and iceberg calving in real time. Remote sensors pick up subtle shifts in mass balance, offering early warnings of instability in regions once thought permanent. International collaborations unite researchers from dozens of nations in projects like the Scientific Committee on Antarctic Research, sharing data to build models of planetary change. And so, Antarctica remains a continent of paradox, at once an ancient vault of Earth's past and a sentinel of its future, a place of serene beauty and hidden tumult. Its silent ice conceals stories of verdant ages, heroic exploits, and scientific revelations yet incomplete. To stand on its freezing shores is to touch a timeless canvas, each crystalline flake a brushstroke in a masterpiece that invites endless exploration and whispers of truths still buried beneath the ice. In the drifting hush of twilight, where the sun clings low to the sky, you can almost hear the slow pulse of the ice sheet breathing beneath your feet. Vast rivers of snow grind imperceptibly toward the coasts, conveying weight and pressure in a dance that spans centuries. Across the Polar Plateau, the air shimmers with cold, refracted gleams that turn each snowflake into a tiny prism. Here, silence is a companion, and in that silence, the land reveals its ancient secrets. Vast moraines of rock fallen from crags now hidden by centuries of snowfall. The fossilized remnants of forests once green, and the tremors of a world in constant, if glacial, motion. Beneath this realm of white, the crust of the earth responds to the colossal weight above. In places, the bedrock dips hundreds of meters below sea level, forming basins that cradle subglacial lakes like deep-set gems. Lake Willans, for instance, lies tucked under some 800 meters of ice, its dark waters warmed by geothermal heat. When its volumes shift, sometimes draining, sometimes refilling, they reverberate through the ice sheet, triggering subtle movements that can ripple far afield. Sensors placed on the ice detect these whispers, translating them into data streams that speak of hidden currents and frozen tides. Not all movement is slow. In the Antarctic Peninsula, where the ice meets the warmth of ocean currents, ice shelves extend outward before collapsing with dramatic suddenness. The Larsen B ice shelf, a massive tongue of ice that once stretched for thousands of square kilometers, gave way in a matter of weeks, calving into countless berg fragments that glittered under the sun like shards of glass. Such events remind us that within the ice's seeming immortality lies a fragile equilibrium, easily disturbed by shifting climates and changeable seas. Away from coastal breakdowns, the heart of Antarctica remains a realm of delicate balance. Wind shapes the ice into rippling dunes and sculpted cornices, carving patterns that shift with every gust. These katabatic winds, cold air flowing down the slopes under gravity's force, can gust at hurricane speeds, biting through layers of clothing and silencing even the mightiest of engines. In their wake, they polish the ice into smooth expanses, erasing footprints and transforming the landscape into something ever more pristine, ever more alien. Yet life, resilient and gentle, finds a way. Beneath the waves, krill gathers in vast shoals, feeding on phytoplankton nourished by upwelling currents. These tiny creatures, no larger than a thumbnail, form the foundation of a food web that supports orcas gliding through gray waters, elephant seals basking on ice floes, and emperor penguins huddling against the freeze during months of perpetual night. Their communal warmth, hundreds of birds packed together in rhythmic undulations, becomes a living tapestry of survival and ecosystem that thrives on the margins of possibility. On the surface, research stations stand as islands of warmth and light against the endless white. At Neumayer Station 3, Squat and aerodynamic, wind whistles through instrument towers that measure ozone, carbon dioxide, and cosmic rays. At Concordia, the solitude presses in as scientists live for months without relief, studying the auroras that dance overhead and the meteorites that fall, some older than human history itself. Each station is a microcosm of humanity's longing to understand. Power generators hum, 3D printers whir, and satellite dishes point skyward, connecting this remote world to the broader tapestry of human knowledge. In every lab, every borehole drilled, and every seismic survey conducted, Antarctica yields new chapters of its story. We learn of iron-rich dust, blown from distant continents millennia ago, fertilizing ancient oceans. We uncover layers draped with tephra from volcanic eruptions, marking cataclysms that reshaped climates worldwide. We probe the magnetic signatures frozen in ice crystals, mapping the wanderings of Earth's magnetic poles across epochs. Each discovery is a pebble dropped into a still pond, its ripples reshaping our understanding of Earth as a living system, dynamic, interconnected, and forever changing. As you breathe in this world of ice and wind, let your thoughts drift on the currents of time. Feel the weight of centuries in each snowflake, sense the slow convulsions beneath the ice, and listen to the muted symphony of a continent that reveals itself only to those patient enough to wait. Here, in the hush of frozen expanse, lies a story that moves not in dramatic leaps but in gentle, unceasing flower story of ancient forests, silent lakes, drifting bergs, and the indomitable persistence of life even amid the most unyielding cold. Somewhere beyond the horizon, where sky and ice blur into the faintest whisper of gray, lies the dry Valacen oasis of rock and dust, untouched by glaciers for millions of years. Here, wind scourges the ground so relentlessly that no snow can accumulate, leaving behind barren canyons etched with millennia of erosion. Streams fed by seasonal melt trickle only in the brief austral summer before vanishing, their channels carved into sandstone walls like veins in an ancient hand. In this stark desert, life clings to life in microscopic communities. Cyanobacteria form crusts on stone, and tardigrade hardy creatures enter suspended animation to endure the extremes. As you drift farther south, the ice sheet rises, climbing toward the pole like a vast, frozen cathedral. At Dome A, nearly 40 meters above sea level, stations perch in skeletal white shelters, with research crews enduring air so thin each breath becomes a deliberate act. They study cosmic microwave background radiation, peering back to the universe's infancy, and they drill cores that stretch ever deeper into the planet's memory. With each meter removed, they encounter snow compressed into ice that fell in ages unimaginable, harboring isotopic clues to temperatures from long before humans walked the Earth. Meanwhile, seismic networks planted across the ice listen for rumblings of the hidden world beneath. In 2010, scientists detected low-frequency tremors that hinted at a network of subglacial lakes connecting like hidden rivers. These aqueous highways may transport nutrients and even organisms, forging a secret ecosystem in darkness and pressure ray realm, where life, if it exists, has evolved in isolation for untold epochs. Such discoveries inspire both wonder and caution. What pathogens or unknown life forms might lie concealed? And what lessons could they teach us about resilience in the face of extremes? On the margins where land meets sea, ice cliffs tower hundreds of meters above churning waters, their faces striated with layers of ancient snowfall. Calving icebergs break free with thunderous booms that echo off distant ridges, sending shock waves through the water and reshaping the coastline. These drifting giants, some the size of small states, carry with them geological and biological treasures, rock fragments embedded in the ice, and nutrients trapped in the frozen matrix that, once released, nourish plankton blooms in open water. Surrounding Antarctica, the Southern Ocean churns with currents that encircle the globe. The Antarctic Circumpolar Current is the world's most powerful marine conveyor belt, transporting cold water eastward and redistributing heat, carbon, and nutrients. It acts as a barrier, isolating the continent's climate and maintaining the extremes that define the polar world. Yet it also links ecosystems, carrying seals and seabirds on migrations that span hemispheres and ferrying microscopic organisms that anchor food webs from the coast to the deep sea. Above, the polar sky shifts in mood, from brilliant blues to tenebrous nights punctuated by stars and aurora. When the sky darkens, the southern lights unfurl like ribbons of silk, flowing in emerald and violet across a canopy of endless black. In these moments, time seems to loosen its grip, and the frozen landscape becomes a stage for a cosmic balletin ephemeral performance that reminds us how small and fleeting our own lives truly are compared to the grandeur of the polar realm. In the soft, drifting snow and the deep, hidden waters, Antarctica invites contemplation. It is a place of extremes of silence and storm, of warmth beneath the ice and chill above it, of microscopic life in a desert of frost and gargantuan icebergs adrift at sea. As its story continues to unfold, we listen with rapt attention, for in every crack, every core, every quivering aurora lies a verse in an epic as timeless as the ice itself. Far to the west, the Ellsworth Mountains thrust their dark silhouettes against the pale sky, a spine of granite and gneiss that predates the ice itself. Their peaks, named for explorers of old and mythic figures, bear scars of ancient glaciation cirques and arêtes, carved by tongues of ice long vanished. In summer, weather stations there record surprising warmth as solar radiation bakes the exposed rock, driving snowmelt that seeps into fissures and refreezes in nightly cold to pry loose great slabs. This freeze-thaw cycle, though subtle, shapes the mountains slowly, depositing talus at their feet and revealing fossils of marine creatures from when these heights lay beneath prehistoric seas. Across the Antarctic plate, the transantarctic mountains form a vast divide between East and West Antarctica. They guide the flow of ice, channeling enormous glaciers like the Beardmore and Shackleton toward the Ross Sea. These ancient rivers of ice, kilometers wide, grind steadily onward, their basal ice sliding on meltwater and rock debris in a process akin to lubrication beneath a colossal machine. Crevasses gape at their margins, jagged reminders of the immense stresses within, while on their surfaces, snow bridges form delicate arches that collapse without warning under the weight of explorers or machines. East of the divide, the mysterious Dome Sea rises, its summit an expanse of pure white that reflects the sun's rays with blinding intensity. Here, researchers drill for cosmic dust, trapped in layers of ice, seeking tiny particles that drifted through space before embedding themselves in snowfall. Each grain tells a story of supernovae, of interstellar clouds, and of comets that once swept near Earth. In these silent drills, humanity reaches back to touch the universe's earliest moments, guided by sunlight refracted through ice, and by our longing to understand the sky we share. While scientists probe upward and outward beneath the ice, enigmatic rivers wind towards sudden drops. Radar surveys have mapped channels carrying water from the Gamburtsev Mountains to the coast. One such conduit, nearly 20 kilometers long, transports meltwater from the interior to subglacial lakes and, in places, out to ice shelves, lubricating basal plains and influencing flow rates. It's a secret plumbing system, buried under kilometers of frozen armor, that mirrors the veins of the living Earth above water's surface. Flow paths shift with seasons and decades, and as temperatures change, their behavior may hasten ice loosened with it. Global sea levels. At the fringes, where ocean meets ice, tidal forces flex the ice shelves, causing them to rise and fall by meters daily. This rhythmic motion cracks the ice, forming fractures that spiderweb toward grounding lines where the ice meets bedrock. In spring, as the sun returns, meltwater ponds collect on the surface of the shelves, seeping into crevasses and prying them open further in a process called hydrofracturing. When enough water accumulates, the shelves can shatter, unleashing cascades of bergs that accelerate the flow of inland ice toward the sea. Scientists monitor these processes with satellites and on-site GPS stations, aware that once certain thresholds are crossed, the retreat may become unstoppable. Throughout the continent, radio telescopes perched on domes listen for whispers from deep space, taking advantage of the thin, dry air to capture signals obscured elsewhere by moisture. At Ridge A, one of the coldest spots on Earth, atmospheric water vapor plummets, offering extraordinary clarity for astronomers. Here, sky and ice converge to create observatories that peer billions of light-years into the cosmos, as if Antarctica itself were a bridge between Earth's ancient past and the farthest reaches of time and space. Yet, for all its extremes, Antarctica remains accessible to experienced researchers, to national programs, and, increasingly, to tourists. Icebreaker cruises land visitors on drifting ice floes, where they meet colonies of Adelie penguins courting and leaping from the water in graceful arcs. Hiking parties cross moraine-strewn valleys to gaze at meteorite fragments in the dry valleys, remnants of asteroid impacts from long before humans gazed at the heavens. Even on these brief visits, travelers sense the fragility beneath the grand vistas. Footprints melt into the snow, dyes fade in ultraviolet blasts, and waste must be craned out to keep the continent pristine. Human footprints aside, the wild heart of Antarctica continues its quiet rhythms. Subglacial lakes refill, ice streams pulse and stall, and volcanoes whisper through thermal anomalies detected from space. The continent's glaciers crack and melt in places, yet grow thicker in others as snowfall patterns shift. Every change, no matter how small, weaves into the global story. Sea levels inch upward, ocean currents adjust, and even distant climates respond to the ebb and flow of ice at Earth's southernmost edge. Imagine descending into one of the hidden basins beneath the ice, where darkness is absolute and silence profound. A narrow borehole, just wide enough for instruments, pierces the sheet to reveal a world of black water and rock walls slick with mineral deposits. Remotely operated vehicles, bathed in narrow beams of light, drift across the liquid mirror, mapping the terrain and sampling water that has never seen the sun. In these depths, scientists search for extremophiles microbes adapted to darkness, pressure, and cold, their metabolisms hinting at how life might endure in the icy moons of Jupiter or Saturn. Above, the sky shifts with seasons. In summer, the sun circles the horizon without setting, casting long, low rays that gild the ice in rose and gold before dipping below the farthest ridges. Snow crystals sparkle like diamonds, and the world feels boundless. In winter, darkness descends like velvet, broken only by the aurora australis and by occasional flares of meteorites blazing through the atmosphere. Observers wrapped in insulated parkas stand beneath the lights, feeling the hush press in, aware that the nearest human neighbor may be thousands of kilometers away. Life's stubborn sparkle appears wherever conditions allow. On coastal rocks warmed by sun and salt spray, mosses and algae cling in slimy mats, their chlorophyll green stark against gray stone. Inland, cryptogamic soils host bacteria and fungi that digest trace nutrients, creating dark patches in the snow where they thrive. Seabirds wheel above the breakers, and in the water below, colossal squid drift in eternal twilight, ghostly leviathans rarely glimpsed but suggested by the scars on whales and by jumbo beaks caught in floating carcasses. Geologically, Antarctica is a mosaic of ancient cratons and younger terrains, stitched together by tectonic sutures that tell tales of continental collisions and suturings. East Antarctica's core dates back billions of years, part of the stable nucleus of Gondwana, whereas West Antarctica is a jumble of island arcs and oceanic fragments more recent in origin. Between them, the Ross orogenic belt tells a story of mountain building and subduction, now buried deep under ice, yet still registering in gravimetric maps and in the grade of metamorphism in exposed rocks. The interplay of ice and rock is evident in the coastal fjords of the Antarctic Peninsula, where U-shaped valleys harbor deep waters, enabling warm circumpolar currents to intrude beneath ice shelves, melting them from below. This undercutting weakens the shelves and sets the stage for sudden collapses. In places where glaciers meet the sea directly, the fronts stand as towering walls with streaks of blue icy ancient snow compressed into solid bubble-free blocks that glow like sapphires when sunlight penetrates. Each crevasse and serac hints at the glacier's hidden dynamics, flowing slowly outward, turning ice into liquid through friction and pressure, and replenishing the ocean with fresh water that influences salinity and thermohaline circulation. Amid these processes, researchers deploy autonomous sensors on drifting flows, beneath ice shelves, and through boreholes. They send data via satellite to analysis centers worldwide, creating real-time models of ice motion, temperature gradients, and melt rates. Glaciological models incorporate these observations to forecast contributions to sea level rise, while ecological studies track krill populations through sonar nets and DNA sampling, revealing shifts in abundance linked to changing sea ice extent. Through all this, Antarctica serves as both laboratory and litmus test gauge of planetary health, and a laboratory for understanding extremes. It reminds us that Earth's climate is a delicate web, responsive to perturbations in the remotest corners. And it whispers to us of futures yet unwritten. If warming persists, the ice sheet may shed mass more rapidly, raising seas and redrawing coastlines. If protections hold and emissions fall, the balance may stabilize, preserving this vast white wilderness for centuries to come. So let yourself drift on this narrative of ice and stone, of hidden lakes and soaring peaks, of silent depths and cosmic vistas. Feel the pull of Antarctica's mysteries, of life's persistence, and of forces that shape our world on timescales beyond human lifetimes. In its frozen heart lies a story of transformation, of supercontinents parted, of forests buried and reborn beneath ice, and of a planet ever in motion. And in that story, we find echoes of our own fragile existence, beckoning us to listen and to learn from the slow, ceaseless rhythms of the southernmost continent. Far from the beaten paths of research stations and tourist landings, the Amundsen Sea sector lies cloaked in deep indigo twilight, its ice streams flowing swift and silent toward the open ocean. Here, the Pine Island and Thwaites glaciers, dubbed the Doomsday glaciers, by some scientists slip inexorably seaward on lubricated beds of meltwater. Their grounding lines, once anchored on shallow seabeds, are now retreating into ever deeper troughs, where warmer circumpolar currents nibble at ice from below. The result is a hidden ballet of ice thinning, ice acceleration, and iceberg calving that can occur in sudden pulses, reshaping the coastline in a matter of years rather than centuries. Unmanned submersibles have peered beneath these floating margins, revealing walls of blue ice towering above a labyrinth of cavities carved by swirling meltwater, evidence of the powerful under-ice currents reshaping the continental frontier. Yet even as these giants shift, life in the surrounding waters persists with astonishing vigor. Seabed surveys have unveiled rich benthic ecosystems flourishing in the nutrient-laden upwellings off the Amundsen Shelf. Soft corals and sponges, some centuries old, anchor themselves to rocky outcrops, while starfish and brittle stars carpet the depths in slow-motion mosaics. In surface waters, penguin colonies cling to shrinking sea ice floes, their chicks huddling against the cold while parents forage hundreds of kilometers offshore. Each return to the rookeries is a test of endurance, as adults navigate shifting pack ice and dwindling krill stocks, returning with gaping beaks full of nourishment for chicks whose downy feathers promise future survival. Above the shoreline, seasonal meltwater carves ephemeral rivulets through scree and sand, collecting in shallow ponds that mirror the sky. These oasis-like habitats, though fleeting, support colonies of brine-tolerant algae that bloom in bright green mats, transforming the monochrome landscape with momentary flashes of life. Scientists sampling these ponds have discovered unique microbial communities, some entirely new to science. Their DNA encoding enzymes that function at extremes of salinity and temperature molecules, with potential applications in medicine and biotechnology. While surface processes capture attention, the continent's interior continues its slow dance of isostatic adjustment. As ice mass is lost, the underlying crust rebounds upward, a phenomenon known as post-glacial rebound. GPS stations across East Antarctica detect millimeter-scale uplifts each year, a reminder that the land under the ice is as dynamic as the ice above it. Over millennia, Such rebound can raise previously submerged terrains, exposing ancient shorelines and fossilized remains of long-extinct marine life, allowing geologists to reconstruct past sea levels and refine models of glacial history. In the heart of the ice sheet, the Polar Plateau rises to heights exceeding 500 meters, where atmospheric pressure drops low enough that water boils at temperatures barely above freezing. Here, the air is thin, cold, and supremely dry conditions, so austere that only the hardiest of microorganisms eke out a living in thin films of moisture around mineral grains. Yet even at these elevations, LiDAR surveys have captured erosional features carved by ancient katabatic winds, patterns that hint at periods when the plateau may have been nearly ice-free. Its barren surface swept by relentless gales, resembling the lunar highlands more than the white desert we know today. The connection between Antarctica's frozen interior and the world beyond is woven through global climate. Ice core records from Dome Fuji and the newly drilled Roosevelt Island cores extend the atmospheric archive back over 1 million years, tracing the rhythm of ice ages, interglacial warmth, and dramatic swings in greenhouse gas concentrations. Each new core provides finer resolution, revealing subcentennial oscillations, short-lived warm spells, or abrupt coolings, insights that can sharpen our understanding of potential tipping points as humanity alters the atmosphere with unprecedented speed. Throughout the continent, autonomous observatories stand sentinel. Buoys drift within polynyas, open water oases, amid sea ice measuring salinity, temperature, and nutrient flows, feeding data in real time to oceanographers modeling Antarctic bottom water formation. These dense water masses, born in the polar crucible, sink and travel along the ocean floor, ventilating the deep sea and influencing global thermohaline circulation. Minor changes in their formation rate can ripple through ocean heat distribution, with implications for climates far from the poles. Despite the formidable isolation, the human footprint in Antarctica grows ever more interconnected. Ice-tethered drones map crevasse fields by day and night, while satellites equipped with synthetic aperture radar pierce cloud and darkness to chronicle surface changes. Back at home, supercomputers assemble petabytes of data into simulations that project the continent's future under various warming scenarios. Interdisciplinary teams, glaciologists, oceanographers, biologists, and atmospheric chemists weave their findings into policy advisories, urging international cooperation to curb emissions, protect marine reserves, and uphold the treaty's spirit of peace and science. And yet, for all the science and scrutiny, the mystique of Antarctica remains untamed. In its silent wastes lie stories of worlds past and futures, yet uncharted. Each crack in the ice shelf, each calibration of an infrared sensor, each triumphant discovery of a new bacterium in a hidden lake, adds a verse to a saga spun from water, rock, air, and time. Here, at the bottom of the world, we confront the delicate balance of nature, fragile, dynamic, and profoundly interconnected with the fate of every living thing above and beyond the ice. As the austral summer fades, twilight returns in a slow waltz, extending the shadows across the ice, until the continent once again slips into 6 months of dusk. At research stations, autumnal routines begin. Generators are winterized, supply caches checked, and flight paths over sea ice planned for the sparse days when planes can land. Personnel rotate out, their departure leaving behind empty bunk beds and the hum of scientific instruments as the sole companions of the winter cruise. Above, the ozone hole reaches its peak, a vast ultraviolet gateway that, despite international bans on CFCs, continues to reopen each season before healing as spring arrives. During the long night, scientists hunker down to analyze the season's data. Meteorological balloons ascend into the black heavens, trailing radiosondes that measure temperature, pressure, and humidity through the troposphere and beyond. Data from these flights feed into global weather models, improving forecasts for faraway regions that experience weather patterns seeded by Antarctic cyclones and air masses. Meanwhile, ice-penetrating radar surveys conducted from the safety of oversnow vehicles map hidden crevasses and detect basal channels that could feed new subglacial lakes, guiding future drilling efforts. In the darkness, biological clocks slow. Emperor penguins huddle in tight spirals on sea ice, their cream-colored chests pressed against one another for warmth. Chicks, still downy and gray, burrow under their parents' feathers, trading places between the chilly edge of the huddle and the balmier core. The communal heat, a mechanism perfected over millennia, allows both parents to forage alternately in iron-rich waters, ensuring the next generation endures until spring's thin ribbon of sunlight returns. Meanwhile, beneath the ice shelves, autonomous underwater vehicles patrol corridors of twilight. Equipped with sonar, sampling arms, and cameras, they record the health of ice-water interfaces, observing melt rates and cataloging microbial mats thriving on near-freezing mineral-rich currents. Their logs, transmitted via acoustic modems to receivers embedded in the ice, traverse data pathways that eventually reach scientists eager for insight into how ice shelf integrity may evolve as the planet warms. Geochemists in isolated laboratory modules analyze samples brought up from subglacial lakes and deep cores. In sterilized environments, they search for biological markers, lipid fragments, DNA fragments, isotopic ratios that speak of metabolic pathways adapted to high pressure, low nutrients, and perpetual darkness. Each positive signal hints at ecosystems shaped in isolation, where energy may derive from chemical reactions with rock and hydrogen gas liberated by water-mineral interactions. These findings resonate far beyond Earth, informing astrobiologists pondering life's potential on Jupiter's moon Europa or Saturn's Enceladus. As spring's light inchingly brightens the horizon, the continent stirs. Snow melts reveal familiar landmarks, the jagged peaks of the Queen Maud Mountains, the serrated ridges of the Pensacola Range, and the gentle curve of ice streams feeding the Weddell Sea. Field teams prepare to deploy GPS drifters on shrinking ice floes, tracking their journeys before eventual breakup. Biologists ready nets for krill surveys in newly opened polynyas, charting the pulse of life that awakens with the returning sun. Amid these flurries of activity, policy discussions unfold in distant capitals. Antarctic governance hinges on science-informed diplomacy, balancing conservation goals with the realities of shipping routes, fishing interests, and deep-sea mineral prospecting pressures. Marine protected areas expand in the Ross Sea and planned for East Antarctica, while deliberations consider broader bans on bioprospecting, to preserve genetic resources hidden in the ice. Yet, even as humans debate and deliberate, Antarctica's rhythms remain sovereign. The ice rises, flows, and calves in inexorable cycles. The sky turns from rose to violet to black, and back again in an endless loop. Beneath the surface, subglacial waters surge and recede. Life blooms, hides, and endures in niches of possibility. And in these interwoven patterns of ice, water, rock, and life, we glimpse lessons of resilience, humility, and wonder. A reminder that on this spinning blue planet, the story of one continent resonates with the fate of all. As the light shifts again toward the austral summer, the continent's rhythms quicken in subtle but vital ways. Melt ponds form upon the ice shelves, their azure surfaces absorbing sunlight and initiating summer's advance from above. Beneath that translucent water, crevasses expand as melt seeps into fractures, fracturing ice from within in a slow, insidious disintegration. Scientists monitor these features by drone, capturing high-resolution imagery of meltwater networks that weave across the shelves like veins, draining into crevasse systems and fueling calving events that send tabular icebergs adrift into the Southern Ocean. Along the coast, research vessels sail into bays once choked with pack ice, deploying oceanographic instruments that profile temperature and salinity at depths inaccessible to earlier expeditions. Moorings placed on the seafloor record currents and nutrient flux, while autonomous gliders ride the thermocline, sampling chlorophyll concentrations to track phytoplankton blooms. These microscopic plants, blooming in spring's warming waters, form the fulcrum of Antarctic food webs, sustaining krill which, in turn, fuel the feeding frenzies of humpback whales, the stealthy hunts of leopard seals, and the aerial acrobatics of diving petrels. Beyond biological surveys, contemporary experiments probe the atmosphere's intimate connection with the ice. High-altitude balloons carry sensitive instruments into the stratosphere, measuring ozone recovery above the polar vortex and tracing the dispersal of trace gases emitted thousands of kilometers away. Ground-based LiDAR stations track aerosols lofted by mid-latitude wildfires, which can darken snow surfaces and accelerate melt when deposited atop the ice. Each data point threads into a global tapestry. How distant human activities leave fingerprints on the whiteness of Antarctica, altering its reflectivity and affecting energy balances at the Earth's poles. In the hinterlands, long-range traverses deploy ground-penetrating radar and gravity sensors to refine maps of subglacial terrain. Mobile camps march across the plateau, hauled by tracked vehicles, laying a path through knee-deep drifts to install seismic nodes that will detect the snarl of ice quake-small tremors generated by basal slip or crevasse formation. These networks reveal the dynamic interplay between ice and bedrock, pinpointing regions where basal melt lubricates fast-flowing ice streams, and where colder basal temperatures keep the ice sheet anchored in place. Meanwhile, the human dimension of Antarctica evolves. Tourist numbers, while regulated, have grown as visitors seek first-hand experience of its stark grandeur. Environmentally conscious itineraries emphasize minimal impact. Inflatable zodiacs land on designated beaches. Guests step only where footprints melt within hours, and all waste is carried away. Lectures aboard ships educate travelers on the nuances of Antarctic law, the fragility of local ecosystems, and the global significance of ice loss. In these moments of shared wonder, casual observers glimpse the planet's vulnerability and the interconnectedness of human choices and polar processes. Across the ice, emerging technologies reshape the possibilities of exploration. 3D printed laboratories rise from prefabricated materials, their structures optimized for insulation and modular expansion. Solar panels and wind turbines, tested in cocktail of frigid gales and polar night, demonstrate renewable energy potential to power stations with minimal carbon footprints. Even the humble snow vehicle evolves. Hybrid diesel, electric snowcats, and autonomous surface vehicles scout ahead on long routes, mapping hazards in real time and conveying supplies to field parties with fewer risks to human life. Yet, as innovation opens new frontiers, the specter of climate change looms. Projections indicate that under high-emission scenarios, coastal regions may shed ice at accelerating rates, contributing centimeters of sea level rise within decades. Thwaites Glacier, once considered slow-moving, shows signs of irreversible retreat, a gateway to West Antarctica's deep basin, which, if fully destabilized, could raise global sea levels by more than half a meter. International research programs intensify their focus here, drilling boreholes to deploy thermal sensors in the glacier's bed, hoping to understand the processes of ice thinning and whether engineered interventions such as underwater berms to block warm currents could delay collapse. As these efforts proceed, policymakers and scientists convene regularly under the Antarctic Treaty System. Climate negotiators review the latest findings, crafting resolutions to expand marine protected areas and limit harmful activities. The Commission for the Conservation of Antarctic Marine Living Resources assesses fishery quotas to preserve krill stocks vital to the ecosystem. Environmental assessments become more rigorous, balancing the need for science with the imperative to safeguard the wilderness. In the quiet of a summer's evening, when the sun dips low yet never fully sets, the continent feels simultaneously static and alive. Ice flows at speeds measured in meters per year, while microbial mats bloom in transient streams. Ice shelves crack and bergs calve, reshaping coastlines inch by inch. And humanity, from specialist scientists to curious tourists, participates in this unfolding saga, studying it, cherishing it, and wrestling with the implications of our global footprint. In the heart of winter's long night, when darkness reigns and temperatures plunge below 80 degrees Celsius, the stations become enclaves of camaraderie and challenge. Teams of scientists and technicians maintain the pulse of research, repairing generators, recalibrating instruments, and passing time with games and storytelling under the dim glow of safety lights. Communication satellites deliver snippets of email and occasional calls home, but the real world feels distant, replaced by the immediacy of data streams and the shifting geomagnetic storms that paint the sky with dancing ribbons of color. On clear nights, radio astronomers at the pole station train their dishes on the faint whisper of hydrogen clouds and pulsars spinning light years away. Interferometry arrays combine signals to peer into galaxies in formation, taking advantage of the minimal radio frequency interference at the bottom of the world. Astrochemists analyze samples collected from the stratosphere for cosmic dust and interstellar molecules, speculating on the chemistry that once percolated through the molecular clouds from which our solar system coalesced. Meanwhile, glaciologists at remote camps continue to pry into the ice's secrets. With hot water drills, they bore shafts hundreds of meters deep, suspending sensors to record temperature profiles and basal water pressure. These boreholes also serve as conduits for modern fiber optic cables distributed temperature sensing systems that can detect meltwater intrusions and refreezing events in real time. In tandem, remote spectrometers survey surface albedo, watching for subtle changes as snow metamorphoses under the influence of wind, sun, and dust deposition. The story expands beneath the waves as well. Submersibles launched from icebreakers carry multi-beam sonar to chart the seabed, revealing canyons carved by ancient meltwater floods and volcanic seamounts cloaked in orange sponges and black coral. Chemosynthetic communities cling to hydrothermal vents, sustained by mineral-rich plumes gushing from the Earth's interior. These deep ocean oases, far removed from sunlight, echo the adaptations of subglacial lakes organisms, exploiting chemical energy sources in perpetual darkness, underscoring life's tenacity in extreme isolation. Above the ice, aerogeophysical surveys crisscross the continent. Aircraft equipped with lasers and radar map surface elevation changes with millimeter precision, choreographing flight lines hundreds of kilometers long. Each overflight adds strokes to a high-definition portrait of ice dynamics, capturing seasonal flexure, snow accumulation, and the subtle sag of the ice sheet under tidal forces. Combined with satellite altimetry, these measurements feed into digital elevation models that faithfully recreate Antarctica's contours in three-dimensional detail. In laboratories scattered across the globe, researchers synthesize these disparate threads into integrated models. Climate simulators couple atmospheric, oceanic, and cryospheric processes to project ice sheet responses under varying greenhouse gas scenarios. Ecological models forecast adaptations of krill and penguin populations to shifting sea ice patterns. Geological reconstructions replay the breakup of Gondwana and the formation of the transantarctic mountains, folding deep time into our understanding of present-day changes. Amid these vast undertakings, educational programs bring the continent's lessons to classrooms far from its shores. Virtual reality experiences, built from drone footage and 3D scans, allow students to walk on sea ice and peer into crevasses. Citizen science projects enlist global volunteers to classify iceberg shapes in satellite imagery, helping scientists track calving events. Through these connections, Antarctica's remote story becomes personal, fostering a sense of stewardship that transcends geography. Ultimately, the tale of Antarctica is one of contrast, of stillness and motion, barrenness and life, ancient origins and unfolding futures. It is a narrative written in ice and seawater, in data points and digital maps, in the whispered conversations of microbes beneath kilometers of frozen armor. To listen to that story is to recognize that Earth's extremes are not remote curiosities, but integral chapters in the saga of our Planeta saga, whose next pages depend on choices made far beyond the continent's icy fringes. Far from the coastal fringes, where the ice sheet ascends toward its highest summits, the bedrock beneath tells stories older than the mountains themselves. Geophysical surveys have mapped vast expanses of crystalline Cratton ancient continental cores that have remained intact for billions of years, interrupted by sutures where tectonic plates once collided. These deep foundations, hidden beneath kilometers of frozen veneer, retain magnetic signatures that chronicle the wanderings of Earth's magnetic poles and the assembly of supercontinents long dissolved. In these hidden depths, heat from Earth's mantle rises unevenly, producing geothermal hotspots that locally thin the overlying ice and feed subglacial rivers. These molten veins, flowing in darkness, lubricate the glacier bed and occasionally erupt in subglacial volcanism, producing local sudden floods that surge beneath the ice, cracking it from below and reshaping in glacial channels. On the surface above, the ice responds in kind. Satellite altimetry reveals subtle domes and depressions where basal melting or freezing dominates, guiding the ice's flow like unseen currents. In places where geothermal flux is high, the ice sheet base hovers at the melting point, producing cushion-like pockets of water that allow the ice above to accelerate in narrow corridors known as ice streams. These ice streams, such as East Antarctica's Recovery Glacier, funnel vast volumes of ice toward the coast, carving out troughs hundreds of meters deep. Along their margins, shear heating warms the ice, creating bands of soft, deformable ice that contrasts with the rigid, cold ice of the higher plateau, duality of strength and yield that sculpts the glacial landscape over millennia. Above these dynamic flows, the surface snow metamorphoses under the influence of wind and temperature. Firn partly compacted, snow gradually densifies into glacial ice, trapping air bubbles that become time capsules of past atmospheres. In the high interior, where accumulation is minimal, the firn layer can persist for centuries before closing off, preserving delicate chemical signals of dust, volcanic aerosols, and past greenhouse gas levels. Researchers drilled deep ice cores at sites like Dome B and Conan Station to retrieve these silent archives, slicing them into sections that yield continuous records of abrupt climate shifts, such as the Dansgaard-Oshger events rapid warming episodes that punctuated the last glacial period. In coastal embayments, tides propagate beneath floating ice tongues, flexing them in a daily cycle that can strain the ice shelf far beyond its yield strength. These flexures generate tidal cracks, which propagate upward into the shelf's interior. During summer, meltwater ponds form atop the shelf and exploit these cracks, promoting hydrofracture that accelerates shelf thinning. The loss of an ice shelf's buttressing pressure can, in turn, trigger inland acceleration of tributary glaciers, amplifying ice discharge to the sea. In this interplay of ocean, ice, and atmosphere, the rhythm of Tedisa force transmitted through hidden channels becomes a driver of continental-scale change. Yet despite these powerful processes, the Antarctic wilderness remains a refuge for life's most tenacious travelers. Along the margins of receding ice, sponges colonize newly exposed seabeds within months, carpeting rocky outcrops with living architecture. Fish species, adapted to sub-zero waters through antifreeze glycoproteins, patrol the depths, while krill larvae ride on spring plankton blooms that surge with daylight. On land, once the ice gives way during summer, moss beds and microbial mats colonize damp depressions, initiating soil formation in a process that may take centuries to yield visible change. Each season's pulse of life, timed to the return of sunlight, underscores the resilience of ecosystems in extremes. In winter's long night, however, the continent retreats into itself. With no photosynthesis to sustain them, surface organisms enter dormancy or perish, leaving only the hardy spores and cysts of microbes to await the spark of spring. Beneath the ice, subglacial microbes feed on chemical energy, dissolving rock minerals to generate life-sustaining compounds. Their existence silent, unseen, and uninterrupted for eons echoes the possibility of life in similarly forbidding environments beyond Earth, from the icy crust of Europa to the frozen methane seas of Titan. In this convergence of geology, glaciology, oceanography, and biology, Antarctica offers a template of Earth's processes writ large and slow. Each year, as the balance between snowfall and melt shifts by a few millimeters, the global sea level responds in kind. Each volcanic tremor beneath the ice whispers of thermal anomalies that could hasten ice retreat. Each advance of the circumpolar vortex shapes weather patterns in mid-latitudes, and each record recovered from the ice's library deepens our understanding of how the planet navigates the delicate dance between cold and warmth, isolation and connection, past and future. As humanity's gaze sharpens on this frozen frontier, the Antarctic Treaty System stands as a testament to international collaboration. Born in 1959 amid Cold War tensions, the treaty pledged the continent to peace and science, prohibiting military activity and mineral extraction while encouraging open data sharing. Over the ensuing decades, it expanded through the Protocol on Environmental Protection, 1991, and the Convention for the Conservation of Antarctic Seals, 1972, erecting regulatory frameworks that balance scientific inquiry with conservation. Management plans designate protected areas from the Ross Sea Marine Protected Area to specially manage sites that harbor vulnerable wildlife, ensuring that research footprints remain minimal and that fragile ecosystems receive sanctuary. Despite these safeguards, the shadow of climate change looms large. Atmospheric warming has been particularly pronounced on the Antarctic Peninsula, where mean winter temperatures have risen by more than 3 degrees Celsius over the last half-century. Ice shelves have collapsed, glaciers have retreated, and species such as the Antarctic toothfish face habitat shifts as ocean waters warm. Conversely, parts of East Antarctica have experienced slight cooling, illustrating the continent's complex response to global forcing. Polar amplification, oceanic teleconnections, and shifting winds conspire to produce patterns that defy simple categorization, demanding nuanced study and adaptive policy responses. In response, scientists and policymakers convene regularly under bodies like the Scientific Committee on Antarctic Research and the Commission for the Conservation of Antarctic Marine Living Resources. They craft harvest quotas for krill fisheries, which, if left unchecked, could deprive whales, seals, and penguins of their primary food source. They explore innovative governance mechanisms, such as the designation of large-scale marine protected areas around the continent's perimeter, and they integrate traditional ecological knowledge gathered from satellite observations, long-term monitoring, and indigenous perspectives on Southern Ocean currento, create management plans that are both scientifically robust and socially inclusive. Technological advances continue to revolutionize our capacity to observe and understand. Miniaturized sensors attached to penguins and seals, logging diving depths, water temperatures, and salinity profiles as the animals forage. Unpowered gliders drift along ocean currents for months, mapping under-ice bathymetry and capturing biogeochemical data in regions too dangerous for ships. High-resolution satellites now detect ice discharge fronts at sub-kilometer scales, enabling near real-time monitoring of calving events. And machine learning algorithms sift through petabytes of imagery, identifying patterns such as early signs of shelf collapse that human eyes might miss. Yet for all the innovation, Antarctica's essence remains unchanged, a place of sublime stillness, of white horizons that stretch to infinity, and of a silence so profound that each whispered breath seems amplified 100-fold. It is a canvas where Earth's past is preserved in frozen form and where its future is being written, line by line, by shifting ice and thawing permafrost. In that grand narrative, we find not only scientific intrigue and geopolitical significance, but also a mirror reflecting our collective stewardship of the planet. So, as you drift deeper into this tale of ice and time, consider the lessons it imparts, that even the most remote reaches of Earth are intertwined with our fates, that slow, imperceptible changes can yield profound consequences, and that in the delicate interplay of forces from the heat of the core to the chill of the outer reaches lies a story both humbling and hopeful. For in Antarctica's silent vastness, we see the blueprint of resilience, adaptation, and the enduring wonder that defines life on this blue world. In the uncharted expanse south of the Ross Ice Shelf, where satellite coverage thins and drones struggle against katabatic gusts, lies a realm that few have glimpsed, the Bentley subglacial trench. Here, gravity pulls the ice sheet down into a trough nearly 500 meters below sea level, making it the deepest land-based point on Earth beneath a cloak of ice. Beneath those kilometers of frozen weight, water and rock press together under immense pressure, and geothermal heat warms the bed enough to keep the interface at or just below the melting point. Radar surveys hint at tangled networks of meltwater carving channels through sedimentary basins, perhaps draining toward subglacial lakes like Savitskaya or Hodgson. In these hidden aquifers, rock fragments erode slowly, releasing minerals and nutrients that, if microbial life exists, could sustain communities in chemical darkness. Above, the ice sheet funnels toward the trench along subtle gradients, forming ice streams that accelerate to speeds of several kilometers per year. Their margins glow slightly warmer on thermal imagery, a testament to friction and basal thaw. Crevasses abound along their boundaries, releasing plumes of frazil, ice, and slush into the subglacial system. Field teams, dropped by ski-equipped aircraft, set up temporary camps on the trench's flanks, drilling boreholes to install seismometers that capture the low-frequency tremors of stick-slip motion at the glacier's base. Each tremor that echoes through the ice provides clues to how the sheet slides, how fast it can move, and how it might respond if the balance shifts toward accelerated drainage. Farther north, the vast plains of Marie Birdland unfold an austere tableau of blue-tinged ice, upthrust by the volcanic peaks of the Executive Committee Range. Mount Sidley, its summit festooned with fumaroles, vents gas into the frigid air, forging ice caves that scientists explore with thermal cameras and gas sensors. These subaerial vents warm the surrounding ice, altering the local stress regime and occasionally triggering small icy quakes that reverberate across the plateau. Geochemical analyses of ice cores near these volcanoes reveal ash layers from past eruptions, evidence that volcanic activity underlies not only West Antarctica's geothermal heat, but also the rhythmic pulses of ice flow in surrounding regions. In coastal zones, the interplay between sea ice and fast ice governs entire ecosystems. During winter's advance, shorefast ice extends outward, forming thick platforms that seal in bays and base-calm havens, where seals haul out and leopard seals patrol beneath the surface. When spring arrives, winds fracture the fast ice into flows that drift away, opening leads in the pack that attract first the plume of exhalations from feeding whales and then the squadrons of petrels and squaws. Scientists aboard icebreakers time their surveys to these transitions, deploying nets and underwater microphones to capture whale song and krill swarms, linking predator movements to the rhythms of the ice. In the peninsulas that arc northward toward South America, the warming trend has exposed Nunatax rock islands previously hidden beneath snow-revealing fossilized forests preserved in permafrost. Paleobotanists extract pollen grains and leaf imprints from ancient beds, reconstructing climates when beech forests crept close to the South Pole. Those data, when combined with ice core temperature proxies, refine models of past greenhouse conditions, illustrating how polar ecosystems responded to warmth. The lessons gleaned underscore that current warming rates exceed those of natural interglacials, raising questions about the speed at which Antarctic ice can adapt or collapse. High above, the stratosphere above Antarctica remains a focal point for atmospheric scientists. During winter, a strong polar vortex isolates the air, enabling chlorine and bromine radicals to catalyze ozone depletion. Each spring, as sunlight returns, the ozone hole enlarges, thinning the protective layer and increasing UV radiation at the surface. Annual measurements by ground-based spectrometers and balloon-borne instruments track the vortex's strength and the rate of ozone recovery, offering glimpses into the success of global policies like the Montreal Protocol, reminding us that actions on one continent can heal or harm the sky above another. Through these nested processes, from the subglacial trenches to the soaring stratosphere, Antarctica teaches us that Earth functions as a system of interlinked components. Changes deep within the ice propagate upward to affect ocean currents, weather patterns, and ecosystems thousands of kilometers away. In the silent expanse, researchers act as interpreters, decoding signals hidden in ice fractures, in volcanic ash, and in the rhythm of migrating whales. Each finding adds depth to our understanding of planetary dynamics and informs efforts to safeguard a region whose stability underpins coastal communities worldwide. Beyond the physical realm, Antarctica cultivates a different kind of exploration, the human spirit tested by isolation and awe. At remote field camps, scientists endure months of perpetual twilight, their routines marked by the rise and fall of fuel usage rather than the sun's arc. Meals of freeze-dried meals and experimental nutrient pastes sustain strength, while shared ritual storytelling under soft LED lights, impromptu musical performances, and handwritten letters exchanged via satellite-forged bonds that transcend nationality and discipline. Psychologists study these crews to understand group dynamics in extreme environments, research that informs plans for long-duration space missions and for potential bases on Mars or the Moon. Art and literature, too, find inspiration in the White Continent. Poets distill the hush of snowfall into metaphors of renunciation and renewal. Painters capture the shifting palette of twilight in brushstrokes of pallid rose and violet. Filmmakers coax out the eerie stillness of ice caves with drones that record the reverberation of each footstep. These creative endeavors bridge the gap between data charts and human emotion, allowing audiences worldwide to sense, however faintly, the scale and the serenity of a land that defies ordinary perception. Economics and geopolitics converge on the perimeter of Antarctica as well. Though mineral extraction remains banned, nations debate the potential of deep-sea mineral prospecting in the Southern Ocean's clarionite-rich nodules. Fishing fleets vie for quotas of toothfish, while conservationists advocate for strict enforcement of catch limits and for the expansion of no-take zones. Satellite monitoring and drone surveillance assist in tracking illegal, unreported, and unregulated fishing, underscoring the challenge of applying rule of law in a vast, remote expanse where sovereign claims are suspended by treaty. Meanwhile, emerging technologies propose bold interventions. Engineers model the feasibility of artificial ice shelf buttressing, installing underwater piers or cooled seawater barriers to slow ice shelf thinning. Others envision seeding clouds to reflect solar radiation, reducing melt rates on vulnerable shelves. These geoengineering schemes spark ethical and environmental debates. Could such interventions protect coastal cities, or might they disrupt unknown ecological networks? The questions raised illustrate that Antarctica's frozen face confronts us with choices about technological reach and ecological responsibility. In education, virtual expeditions open the continent to students in classrooms thousands of kilometers away. Interactive platforms simulate drilling a borehole in ice, analyzing dust layers for volcanic signatures, or piloting a drone over a crevasse field. Citizen science initiatives invite the public to classify penguin species in time-lapse videos, to count iceberg sightings in satellite images, and to model ice sheet behavior in simplified online interfaces. These engagements democratize science, nurturing a generation attuned to the fragility and wonder of polar regions. Ultimately, the story of Antarctica is both an atlas of extremes and a mirror for humanity's aspirations. It reveals how ancient processes sculpt continents, how life persists at thresholds of possibility, and how human curiosity transforms even the most forbidding landscapes into realms of discovery. It warns that shifts in this remote continent ripple through oceans and climates, affecting coastlines and communities worldwide. And it inspires a sense of stewardship grounded in wonder, reminding us that the choices we make in one corner of the globe resonate to its farthest reaches. So, in the hush of falling snow, in the tremor of ice shifting beneath your feet, and in the glow of auroras dancing overhead, listen to the tale that Antarctica tells, a tale of water locked in time, of volcanic fury beneath sheets of ice, of ecosystems climbing out of barren rock, and of a planet alive in ways both visible and hidden. As the ice continues to flow, both above and below, so too does the story flow onward, an unending epic of discovery, resilience, and our shared voyage on this spinning world. Along the western flank of the Antarctic Peninsula, narrow fjords carve into the rock like silver arteries. Here, the interplay of ocean and ice is especially dramatic. Seasonal meltwater cascades down steep cliffs, flooding the fjords with floatable debris and nutrient-rich fresh water. These inputs spark explosive blooms of phytoplankton, transforming the fjords into neon-green cauldrons of life. In turn, krill congregate in enormous swarms, drawing in whales that surface in slow, majestic lunges, and massive leopard seals that patrol the darker depths. Above, snow petrels wheel on thermals rising from exposed rock, their white wings gleaming against basalt walls streaked with iron-red lichen. Beneath the waves, rocky ridges provide shelter for brittle stars and soft corals, while fish adapted to near-freezing temperatures, armed with antifreeze proteins in their blood, glide effortlessly, their scales reflecting the flickering light filtered through drifting ice flows. This peninsula, once attached more tightly to South America, measures the pulse of global warming with startling clarity. Over the past half-century, air temperatures here have risen several degrees, melting ice shelves that once protected glaciers from the sea's erosive power. The Larsen A and B ice shelves disintegrated in dramatic collapses, sending thousands of square kilometers of ice adrift and hastening the retreat of inland glaciers. Scientists visiting these sites today navigate floating rubble fields and chart the scars on peninsular slopes where ancient ice once pressed. Their measurements of ice thinning and glacier acceleration feed into global models, highlighting how localized warming can cascade into planetary sea level rise. To study these changes in granular detail, field teams deploy a suite of instruments on snowmobiles and tracked vehicles. Ground-penetrating radar peers through the surface layers to determine the remaining thickness of remnant ice shelves, while GPS stations record the subtle uplift of bedrock as ice loads shift. Seismic sensors detect the calving event, small quakes that resonate through the fjords when massive bergs break free. Meteorological towers track the influx of warm, moist air from the Pacific, capturing the wind patterns that drive rapid melt in austral spring, when foamy meltwater rivers streak the ice in transient veins of blue. In the skies above, long-range UAVs survey the changing landscape, photographing both the exposed rock and the surviving ice tongues. Their high-resolution imagery reveals not only the current extent of glaciers, but also the emergence of new meltwater channels that drain into hidden lakes atop the ice. During late summer, these lakes can grow hundreds of meters across, their basins bounded by snow walls that collapse when filled, triggering sudden outburst floods that scour the ice surface and carve temporary channels. At sea, ice-strengthened research vessels circle the peninsula's tip, deploying CTD, conductivity, temperature depth, profilers, and submersible gliders into deep waters to trace the intrusion of warm, circumpolar deep water onto the continental shelf. Scientists measure temperature anomalies mere tenths of a degree above freezing, yet such warmth is enough to melt hundreds of meters of ice over months. Moorings anchored to the seabed record tidal currents and temperature fluctuations, revealing how internal waves generated far to the north propagate beneath the ice shelves and deliver pulses of heat that weaken the ice's underside. Meanwhile, ecologists map the shifting habitats of penguin colonies. Gentoo and chinstrap populations respond quickly to retreating sea ice, establishing new rookery sites on exposed gravel bars, while Adelie colonies decline where sea ice vanishes too early, depriving chicks of ice edge protection. Field biologists count nests via drones fitted with thermal cameras, minimizing disturbance and improving accuracy. Their census data, combined with oceanographic measurements, elucidate how changes in ice cover ripple through the food web, affecting species from krill to killer whales. Cultural historians, too, study the peninsula's transformation, piecing together diaries of early explorers who traversed these icebound channels in wooden sloops and motorized launches. Their sketches and logbooks, compared with modern satellite imagery, document how, even in the previous century, the landscape has shifted. Landmarks marked permanent by those pioneers now lie submerged or stranded miles from the ice front, testament to the dynamic nature of the ice-ocean boundary. In this narrow ribbon of continent stretching toward the southernmost tip of South America, the story of Antarctica's response to warming unfolds in vivid colors and palpable motion. It stands as both sentinel and bellwether. What happens here presages changes that will sweep across wider domains, reminding us of ice's power to shape ecosystems, climate, and coastlines. And as researchers trace the fjord's currents and glaciers' scars, each measurement writes another line in the epic of a world rewired by heat, where every degree of change resonates far beyond these bracing shores. Further inland, the Wilkes subglacial basin lies hidden beneath nearly 2 kilometers of icy muted expanse that, if exposed, would reveal a depression larger than France. Radar surveys indicate this basin's bed slopes gently toward the coast, creating a reverse topography prone to marine ice sheet instability. Were warm ocean water to penetrate beneath its grounding line, it could trigger a self-sustaining retreat, allowing the ice above to cascade toward the sea in accelerated flow. To assess this risk, scientists deploy hot water drills to bore through the ice and lower instruments that measure current velocities, basal roughness, and sub-ice temperatures. Their campaigns yield maps of the bed's geometry and hydraulic pathways, illuminating how meltwater circulates in this dark underworld. Above the ice, research stations such as Davis and Casey shoulder scientific programs that span the entirety of Antarctica's environmental tapestry. Atmospheric chemists at Casey analyze aerosol samples for microplastics and fossil fuel residues, tracing the global reach of human pollution to places more remote than mountaintops. They correlate these findings with snow pit samples, showing that microdebris deposits are highest near transient research camps and airstrips, a reminder that even our presence leaves faint footprints on the purest surfaces. At Davis, marine biologists operate under-ice observatories that host cameras and samplers in shallow coastal bays. Year-round, these installations capture images of fish, starfish, and even the elusive nocturnal movements of Antarctic toothfish. Paired with passive acoustic monitors, they record the calls of seals and whales passing overhead, offering year-long datasets that reveal migration timing in response to sea ice fluctuations. Automated feeders dispense tiny nutrient pulses, attracting microorganisms whose growth patterns reflect seasonal shifts in light and ice cover microscopic dramas, echoing the grand cycles of the polar ecosystem. In parallel, astrogeologists at remote Dome Argus send balloons aloft to capture cosmic ray muons passing through the ice, an experiment that uses the sheet as a colossal particle detector. Their findings probe high-energy phenomena in our galaxy, demonstrating how Antarctica's vast ice fields serve as unique laboratories for physics, far beyond glaciology or climate science. Such interdisciplinary ventures underscore that the continent's value transcends any single field, connecting to questions about the universe's fabric as well as Earth's future. To knit these disparate studies into coherent forecasts, international data sharing networks link polar observatories with supercomputing centers. Petabytes of raw measurements ranging from seismic tremors to microbial DNA sequences feed into machine learning algorithms trained to identify early warning signals of ice shelf collapse or ecosystem shifts. Visualizations project these models onto 3D maps and virtual reality platforms, where scientists can simulate what-if scenarios. What if atmospheric CO2 peaks at 550 ppm? What if circumpolar currents strengthen by 10%? How much additional melt would that induce by 2100? Beyond the scientific sphere, these projections inform policy deliberations under the United Nations Framework Convention on Climate Change and the Antarctic Treaty consultative meetings. Diplomats negotiate amendments to fishing quotas, agree on guidelines for remote sensing surveillance of protected zones, and explore establishing a high seas marine sanctuary around East Antarctica. Non-governmental organizations leverage model outputs to campaign for carbon reductions, highlighting that safeguarding Antarctic ice is tantamount to protecting billions of coastal inhabitants from sea level rise. Yet despite the intensifying scrutiny, the primal beauty of Antarctica persists. In the unending glow of summer nights, icebergs drift past telescope domes, their translucent walls refracting starlight into shimmering halos. Hikers on rocky ridges glimpse the yawning expanse of the plateau beyond, a white ocean frozen over silent, intense, and ever-changing. In winter, scientists venture into meteorite-collecting expeditions, combing snowfields where extraterrestrial fragments stand out in stark relief, each a messenger from ancient worlds. In every creek of shifting ice, in each pale ribbon of aurora, in the ghostly silhouette of a solitary seal on a floating floe, Antarctica speaks of extremes and endurance. It is a place where the boundaries between disciplines blur, where the Earth's deep past meets urgent futures, and where human curiosity collides with nature's majesty. As the ice flows, subglacial waters pulse and ecosystems adapt. The story unfolds not in dramatic leaps, but in steady, inexorable motion, a testament to the resilience of both life and planet, and to our responsibility to listen, to learn, and to honor the silent epic locked beneath the ice. In the eastern reaches of the continent, where ice merges seamlessly with sky, lies the vast expanse of drowning maudland, a realm of sprawling ice-covered plateaus punctuated by jagged rock spires called nunataks. Under the midnight sun, these dark peaks cast long, spectral shadows across the frozen plain, their basalt faces etched with striations from ancient glaciers that once surged over them. Today, scientific traverse teams navigate this white desert using GPS and satellite communication, hauling mobile laboratories behind tracked vehicles as they collect snow samples, and measure subtle variations in surface elevation. Their goal is to understand how katabatic winds, descending from the high plateau, sculpt the snow surface into undulating sastrugi-sharp ridges that defy easy travel, yet record wind direction and strength over seasons. Beneath the snow's surface, ground-penetrating radar surveys reveal hidden valleys carved into the bedrock, channels likely forged by subglacial meltwater when climates were warmer. These channels funnel water towards subglacial lakes, such as Sovetskaya and Gamburtsev's source lakes, creating a network of liquid pathways beneath kilometers of ice. In remote camps, scientists deploy autonomous probes into boreholes to measure water flow, temperature, and conductivity, seeking insights into the dynamics of these underground rivers. Their findings could illuminate whether such water networks lubricate the ice sheet sufficiently to accelerate its motion or, conversely, form a stabilizing layer that cushions the ice from abrupt slips. Along the coast of Dronning Maudland, the Princess Ragnhild Coast presents a different tableau. Vast ice shelves, fringed with new-growth krill blooms in summer seas that shimmer with iridescent plankton. Research vessels equipped with CTD rosettes lower sensors through the thermocline to sample nutrients and temperature, mapping the intrusion of warmer currents beneath the floating ice. Biologists aboard these ships deploy plankton tows at dawn, netting swarms of krill whose abundance varies with sea ice concentration and water salinity. Their analyses reveal that even slight increases in water temperature, mere tenths of a degree, can shift krill distribution, with cascading effects on dependent predators, from Adelie penguins guarding rookeries on nearby rocky shores to humpback whales that breach in open water. Further offshore, the Weddell Sea endures its own dramas. Here, fast ice extends from the coast, forming a broad platform that seals off embayments and nurtures colonies of emperor penguins. In autumn, these great flocks gather on stable ice, where females incubate eggs in brood pouches, while males huddle in rotating circles against the cold. Field teams brave blizzard conditions to count nests via high-wing aircraft fitted with infrared cameras, their data crucial for tracking population trends over decades. As sea ice extent fluctuates with changing climate, these counts reveal that some colonies face dwindling breeding grounds, while others adapt by shifting sites farther inland or closer to open leads. Beneath the surface of the Weddell Sea, a different marvel unfolds. The dense, salt-laden Antarctic bottom water, formed in polynyas where water freezes and rejects brine, sinks and spreads northward along the ocean floor. Moorings anchored in deep channels record the passage of these frigid currents, tracking their temperature, salinity, and flow speed. In recent years, anomalies in these readings hint at changes in bottom water formation rates, potentially linked to shifting sea ice dynamics and freshwater input from melting glaciers. Oceanographers model these shifts to predict how Antarctic bottom water circulation might influence global heat distribution and carbon sequestration in the deep ocean. Amid these physical processes, life finds niches both grand and microscopic. Under the Weddell's ice cover, sponge gardens flourish on the seabed at depths beyond human reach, their skeletons forming intricate frameworks that host tiny crustaceans and nudibranch. Microbial mats cling to the underside of ice shelves, drawing energy from organic matter carried down with meltwater. Chemotrophic bacteria extract minerals from rock and ice, producing chemical gradients that sustain miniature food webs. Each discovery underscores the adaptability of life in extreme isolation, and each sample returned to surface labs becomes an ambassador in the broader quest to understand Earth's biosphere limits. Above it all, the southern sky shimmers with auroral arcs, their curtains reflecting off ice surfaces and glacial lakes alike. During the brief twilights of autumn and spring, these lights dance overhead in symphonies of green and violet, moments of beauty that punctuate long days of data collection. Observatories record their spectral properties, linking them to solar wind intensity and geomagnetic activity, while artists document the ephemeral displays in sketchbooks and lenses, blending science and wonder. In these silent nights, researchers pause to gaze upward, reminded that even in this remote expanse, Earth remains intimately connected to the broader cosmos. To the north, the rugged coastline of the Antarctic Peninsula extends like a jagged spine toward South America, its rocky capes and ice-filled channels charted by expeditions hungry for discovery. In this transitional zone between maritime influence and continental interior, weather stations record some of the continent's highest precipitation rata snowfall that deepens inland glaciers and fuels summer meltwater streams. Hydrologists measure discharge from these streams as they carve ephemeral gullies through snowfields, depositing till and rock flour into downstream lakes and fjords. Sediment cores from these basins reveal layers of volcanic ash and dust, each stratum a timestamp of past eruptions and wind patterns from distant continents. Ecologists studying the peninsula's flora and fauna document remarkable resilience. Moss beds, confined to moist microhabitats near meltwater seeps, photosynthesized during the fleeting summer days. Green carpets edging streams, with tiny sporophytes that release spores carried by wind across the stark landscape. Lichen communities colonize bare rock, chemically weathering minerals, and contributing to soil formation, a process measured in millennia yet underway in scattered test plots monitored by automated cameras. In spring, migrating seabirds such as snow petrels and Antarctic terns return to cliffs above breeding colonies, where biologists track nest success in relation to sea ice duration and prey availability. Glaciologists focus on outlet glaciers that flow from the high plateau through narrow ice tunnels and steep chutes, their surfaces crevassed and riddled with moulins vertical shafts funneling surface meltwater to the base. By drilling temperature sensors into these moulins, researchers gauge the heat transfer between water and ice, critical in modeling basal lubrication that may hasten glacier movement. Time-lapse photography captures the formation of seric-storing ice pinnacle sand, their collapse, events that release avalanches of ice and snow into narrow valleys below. These frequent, localized hazards shape the landscape and challenge field safety protocols, reminding teams of the continent's raw power. Offshore, sea ice seasons govern marine life rhythms. Multi-year ice drifts in from the Weddell Sea, forming long-lived flows that provide stable platforms for Weddell seals to haul out during pupping season. From these ice platforms, seals dive hundreds of meters into nearly frozen water, using their whisker-sensitive faces to detect prey in pitch-black conditions beneath the ice. Biologists tag individuals with time-depth recorders that archive dive durations, depths, and water temperatures, mapping foraging habitats and prey fields. Their work shows that seals adapt dive behavior in response to sea ice thickness and prey availability, altering patterns over seasons and years in ways that signal ecosystem health. In parallel, cryosphere scientists investigate permafrost dynamics on the peninsula's low-lying island outposts. Though true continuous permafrost is rare here, isolated patches beneath moss and lichen beds remain frozen year-round. Thermal probes inserted in soil monitor thaw depth, revealing that rising air temperatures contribute to deeper summer thaw processes that, while on a small scale here, mirror concerns in Arctic permafrost regions, where carbon release from thawing soils could accelerate climate change. Comparative studies between polar zones thus weave together narratives of global significance. At the confluence of sea and ice, oceanographers measure turbulence in polynyas-persistent open water areas that form where winds and currents prevent ice formation. Moorings equipped with acoustic Doppler current profilers record high-velocity jets of water that draw heat from deeper layers upward, supporting dense biological communities on shelf seabeds. These polynyas act as oases in winter, where phytoplankton blooms under sea ice seed spring productivity and feed emergent food webs. Satellite imagery tracks their changing extents, providing macro-scale context for in-situ measurements and linking local dynamics to the circumpolar current system. Meanwhile, glaciologists collaborate with oceanographers to deploy subice sensors beneath peninsular ice shelves, tethering arrays of temperature, salinity, and current meters to floating moorings. These arrays reveal strong basal melting where warm circumpolar deep water intrudes through ice shelf cavities, thinning the ice from below. Numerical models assimilate these data to forecast how quickly shelves like Larsen C might disintegrate under continued warming, scenarios that inform global sea level rise estimates and coastal planning efforts. As part of integrated atmospheric studies, meteorologists launch unmanned aerial vehicles to sample air masses above the ice, measuring trace gases, aerosols, and cloud microphysics. These flights profile the boundary layer where clouds form and precipitate, influencing surface energy balance and ice mass gain or loss. Their findings refine climate model parameterizations of polar cloud processes zone of the largest uncertainties in projecting future ice change and underscore the necessity of direct observations in remote zones that supply critical data to global forecasting systems. In every crevasse survey, every oceanographic cast, every biological census on these peninsular shores, the lesson remains consistent. Antarctica's systems are interwoven, from deep geology and hidden waters to surface snow and soaring seabirds. Here, where land, ice, and sea converge under a sky of endless light or unbroken dark, the planet's dynamism is laid bare. The story unfolds in measured steps, glacial pulses, seasonal blooms, atmospheric shifts, each a stanza in the grand epic of Earth's southernmost continent, a testament to the intricate choreography of natural forces and to our enduring quest to witness, understand, and preserve this world of ice. Amid the continent's ceaseless white, the hidden pulse of geothermal heat stirs beneath the ice, shaping landscapes out of sight. In West Antarctica, near the Hudson Mountains and Takahe, satellite gravimetry and airborne magnetometry detect hotspots where mantle plumes rise, thinning the ice above by melting from below. Here, ice streams like the Beinschadler and Cam glide over softened beds, their flow patterns punctuated by stick-slip motion recorded by seismic arrays. These tremors, imperceptible to human senses, reveal how the sheet slides, hesitates, and surges along lubricated plains. Mapping these patterns informs models of potential rapid ice loss, as localized heating could trigger wider destabilization if buttressing ice shelves weaken or grounding lines retreat. On the surface, snow accumulation varies dramatically between windward slopes and sheltered troughs. Isotopic analysis of precipitation captured by automatic weather stations shows that snow sources shift with atmospheric trajectories. Moisture-laden air masses from the Amundsen Sea deposit heavy snows on Marie Byrd Land, while air funneled over the Transantarctic mountains brings dry, frigid snow to the Polar Plateau. These patterns influence the mass balance of the ice sheet regions, where accumulation outpaces melt, add thickness, while areas of net ablation lose ground. High-resolution climate models, downscaled to the continent, simulate these processes to forecast how winds, sea ice extent, and ocean temperatures interplay to determine snowfall distributions under future warming scenarios. Beneath this shifting veneer, subglacial biology whispers its own legacy. Biogeochemical probes lowered into boreholes measure nutrient concentrations: iron, phosphate, methane leaked from bedrock into basal waters. Chemolithoautotrophic microbes exploit these compounds, oxidizing iron and sulfur to harness energy in darkness. Their metabolic byproducts, biogenic gases and organic acids, can alter meltwater chemistry and potentially affect ice viscosity. Though utterly microscopic, these communities entwine with glacial dynamics, reinforcing that life's boundaries extend into zones once thought sterile and inert. At the coastline where ice meets sea, tidal cycles sculpt ice shelf fringes into towering cliffs and delicate arches. High spring tides lift the shelves, extending tidal flexure far inland. When paired with surface warming events, these flexures generate cracks that spiderweb through the ice, sometimes advancing tens of meters overnight. Researchers deploy GPS sensors and tilt meters to capture these rapid movements, correlating them with tide gauges and meteorological records to understand the interplay of oceanic and atmospheric forces in shelf stability. Emerging evidence suggests that areas of the outer shelf, long considered resilient, may in fact be primed for sudden disintegration under compound stressors. In these coastal zones, biologists find refugia of life. Under the protective overhang of ice shelf caverns, filter-feeding ascidians and bryozoans colonize hard substrates, their growth rings preserving records of water temperature and food supply. When sea ice retreats in summer, sunlight penetrates into these twilight habitats, fueling photosynthetic blooms of ice algae that drift on under-ice surfaces. In turn, these blooms feed krill and small fish, which then attract seals and penguins to the ice edge. This under-ice ecosystem, once hidden from view, underscores the importance of ice shelf health to marine food webs and highlights how physical changes reverberate through biological networks. On the broader scale, the Antarctic circumpolar wavea, climatic oscillation propagating eastward around the southern ocean links sea surface temperature anomalies, wind stress, and sea ice concentration in a cohesive pattern. Satellite altimetry, scatterometry, and passive microwave sensors track the wave's progress, revealing how warm pulses can thin sea ice and alter ocean stratification over seasonal timescales. The wave's phase affects precipitation patterns over the continent, generating snow-rich and snow-poor regions that modulate ice sheet mass balance. Integrating these coupled ocean-atmosphere signals into ice sheet models improves the fidelity of future projections, anchoring long-term forecasts in observed variability. Yet despite the planet-scale processes at play, Antarctica retains its most elemental force: silence. In the dead of winter, when the last flights depart and research stations seal their doors, the continent drifts into undisturbed stillness. Snow settles in undulating dunes, erasing tracks left by scientists and wildlife alike. The only sound may be the occasional groan of ice, the whisper of wind across a crest, or the distant crash of a calving bird. In that hush, the narrative of Antarctica's saga of heat and cold, of rock and water, of life in extremis continues, written in imperceptible movements and in the slow artistry of geologic and climatic change. In the vast sweep of East Antarctica's inland reaches, where the ice sheet rises toward its highest elevation, the Polar Plateau unfolds as a realm of crystalline, windswept purity. Here, at sites like Dome Fuji and Ridge A, the air is so cold and dry that researchers call it the coldest place on Earth, with winter temperatures plunging below 90 degrees Celsius. The high-altitude environment poses unique challenges. Snow accumulates so little that stations must periodically adjust their stilts to avoid being buried. Instruments must be insulated against sublimation and frost. And human physiology adapts to the thin air through meticulous acclimatization. Yet this austere plateau is prized for glaciological drilling, cosmic ray observatories, and atmospheric monitoring, thanks to its atmospheric stability and isolation from oceanic moisture. Beneath the surface snow, the fern layer transitions ever more slowly into glacial ice. Here, it may take centuries for pockets of air to close off, sealing bubbles that capture snapshots of ancient atmospheres. At Dome C, a Franco-Italian team recovered an ice core extending 800 years into Earth's past, revealing recurring glacial, interglacial cycles, abrupt warming events, and shifts in greenhouse gas concentrations. These cores, when analyzed for stable isotopes, particulate matter, and trapped gases, offer a continuous timeline of climate variability, including the rapidity of transitions that challenge models calibrated on slower processes. On the bedrock below, seismic experiments detect echoes from the Mohorovičić discontinuity and the mantle's transitions, allowing geophysicists to map the thickness and structure of the crust beneath the ice. Combined with gravity measurements, these studies reveal that East Antarctica's cratonic core is thick and cold, contributing to its relative stability under warming conditions. Yet, even here, geothermal anomalies in places like the South Pole region introduce localized basal melting, feeding narrow subglacial streams that snake toward grounding lines hundreds of kilometers away. Above ground, remote sensing satellites orbit in polar trajectories, outfitted with LiDAR altimeters, multispectral imagers, and synthetic aperture radars. From space, they measure surface elevation changes with millimeter precision, track snow cover extent, and detect subtle shifts in ice velocity. gravimetric missions like GRACE monitor changes in Earth's gravity field, inferring mass loss where ice thins or flows accelerate. These orbital eyes enable scientists to monitor the plateau's stability in near real time, alerting researchers to unexpected shifts such as localized speedups along the Beardmore Glacier corridor or unusual surface lowering at Scott Base. At field camps, air quality sensors sample trace gases methane, nitrous oxide, and ozonato, establish baseline levels in an environment largely untainted by human emissions. These measurements feed into global greenhouse gas inventories, constraining sources and sinks with unprecedented precision. Furthermore, aerosol collectors trap particles lofted by distant continental dust storms or volcanic eruptions, offering clues to atmospheric circulation patterns and to the deposition of light-absorbing impurities that can accelerate surface melt when darkening clean snow. Meanwhile, atmospheric scientists launch tethered balloons carrying meteorological payloads into the near-surface boundary layer. These sondes profile temperature inversions, humidity stratification, and wind shear zones that influence the plateau's microclimate. They link changes in katabatic wind patterns to variations in sea ice extent thousands of kilometers away, demonstrating how oceanic conditions reverberate across the plateau through complex feedbacks of pressure systems and cold air drainage. Even so far inland, life finds micro-refuges. Cryoconite holy cylindrical meltwater ponds formed around dark particles host communities of algae, bacteria, and microarthropods that concentrate in suspended sediments. These microecosystems, heated by sunlight absorbed by dark particles, cycle nutrients and contribute to localized melt enhancement. Research on these holes sheds light on how biogeochemical processes operate at the interface of ice and life, and how simple communities exploit narrow thermal niches in frigid landscapes. In this interplay of ice, rock, air, and life, the Polar Plateau stands as both laboratory and sentinel. Its stability lends perspective to the vulnerability of lower elevations, even as its remote data shape global climate assessments. Each fresh layer of snow, each meter drilled, and each satellite pass adds nuance to our understanding of Earth's cold heart whose slow beats govern sea level change and atmospheric rhythms far beyond its silent white expanse. South of the Transantarctic Mountains, along the edge of the Ross Ice Shelf, the grounding line where grounded glacier ice becomes a float marks, a crucial frontier in ice sheet dynamics. Here, massive outlet glaciers like the David, Bird, and Pine Island in West Antarctica are mirrored by Scott, Beardmore, and Darwin glaciers in the Ross sector. Detailed bathymetric surveys reveal that many of these grounding zones lie on retrograde bed slopes, where the bed deepens inland. This topography predisposes them to marine ice sheet instability. Once warm seawater undercuts the floating ice, the grounding line can retreat irreversibly, allowing upstream ice to flow faster and raise sea levels disproportionately. To monitor these zones, researchers deploy GPS arrays on grounded ice to measure vertical and horizontal motion, as well as time-lapse cameras that record the position of grounding lines relative to seasonal tides. Seismic waves, generated by tidal flexure, illuminate subice roughness and water depth, while radar interferometry from satellites tracks grounding line migration at decadal to seasonal scales. In situ temperature probes detect basal melt rates, and hydrophones embedded in the ice listen to the crackle of ice-ocean interactions each data stream, offering a piece of the puzzle in forecasting ice sheet responses to warming oceans. On the shelf itself, the Ross Ice Shelf extends like a frozen ocean, its surface dimpled by crevasses and smoothed by winds. The shelf buttresses the inland ice, slowing the flow of upstream glaciers by absorbing shear stress. Underneath, slimy biofilms cling to the ice-water interface, where filter feeders and bryozoans colonize the underside, drawing nutrients from the ocean currents. Marine ecologists use ROVs, lowered through boreholes, to photograph these communities, while water samplers profile the mixing of cold meltwater and circumpolar currents that shape habitat conditions. Above the shelf, aerogeophysical flights measure ice thickness, layering, and internal reflections from glacial stratigraphy. These radar reflections reveal annual snow layers, glacial flow disturbances from pinning points, and ancient grounding zone wedges left by past advances. Interpreting these signatures, glaciologists reconstruct cycles of shelf advance and retreat dating back thousands of years, framing contemporary changes within the context of natural variability and anthropogenic forcing. As summer sunlight returns, field teams install autonomous weather stations and seismic arrays on the ice shelf, braced against katabatic gusts that can exceed 200 kilometers h. These stations record temperature, humidity, wind speed, and seismic noise, monitoring shelf flexure under tidal loading and storm surges. Data loggers transmit via satellite to remote analysis centers, where real-time monitoring can detect emerging rifts or accelerated flow, prompting targeted airborne surveys or ship-based expeditions to validate model projections. In the coastal polynyas off the shelf front, open water oases form, where strong winds and currents hinder ice formation. These polynyasmos, notably the Ross and Mertz regions, are sites of intense heat loss, brine rejection, and Antarctic bottom water formation. Researchers aboard ice-breaking vessels deploy moorings equipped with temperature, salinity, and current sensors to quantify water mass transformation rates. Coupled with satellite imagery of sea ice concentration and drift trajectories, these observations illuminate how the Ross polynya fuels the global thermohaline circulation, drawing deep currents upward and sustaining the planet's heat engine. Meanwhile, the human element remains ever present. McMurdo Station, perched on volcanic rock at the edge of McMurdo Sound, bustles through the austral summer as the largest Antarctic community. Here, scientists from dozens of nations converge. Laboratories hum with analysis of ice core samples and ocean water, and helicopters shuttle field teams to remote sites. Despite the bustle, the stark whiteness beyond the station's perimeter offers constant reminder of isolation and scale. Every journey must be meticulously planned, and every bit of waste carried back, preserving the fragile environment that underpins groundbreaking science. Through all these efforts, the story of the Ross sector unfolds as a microcosm of Antarctica's broader narrative. Ice flowing from interior heights to the sea, hidden currents sculpting marine landscapes, life persisting in twilight habitats, and human ingenuity unlocking secrets buried beneath layers of snow and water. It is here, at the interface of ice and ocean, that the continent's influence on global sea levels and climate is most palpably, and where our understanding of Earth's future hangs in delicate balance. Beneath the swirling snowdrifts of East Antarctica's coastal plains, the interplay of land, ice, and ocean continues in rhythms too slow for human perception, yet too profound to ignore. Here, the Van de Kerkhove and Mertz ice shelves hover above frigid waters, their massive tongues of ice shaped by tides and sculpted by hidden currents. By day, the low-angle sunlight filters through the ice, turning its thousand-year-old layers into bands of cerulean and emerald. By night, the same light refracts auroral glows, casting an otherworldly sheen on the underside of bergs calved from the shelves' margins. Oceanographers studying these shelves deploy under-ice autonomous vehicles that thread through labyrinthine cavities, mapping sub-ice bathymetry and measuring melt rates at the ice-water interface. Their sonar profiles reveal channels carved by warm circumpolar deep water narrow, swift flows that snake beneath the shelf, melting its base at rates of up to several meters per year. Microstructure profilers lowered from drifting buoys capture turbulence generated by tidal mixing, showing that periods of higher tides correspond to accelerated melt. These dynamic interactions underscore how even modest changes in ocean temperature can trigger cascading responses in ice shelf integrity, with implications for inland ice flow and global sea level. Farther inland, glaciers like the Denman and Totten press relentlessly toward the sea, their grounding lines creeping into deep troughs that widen beneath the weight of thinning ice. Laser altimetry from polar orbiting satellites tracks subtle changes in surface elevation, indicating whether each glacier is gaining snow or losing mass through melt and calving. Complementing these observations, interferometric synthetic aperture radar measures ice velocity with millimeter precision, capturing seasonal accelerations driven by meltwater percolating through crevasses to lubricate basal ice. As melt seasons lengthen under warming skies, these pulses of faster flow become more pronounced, suggesting that some of the continent's largest outlet glaciers could enter phases of sustained retreat. In coastal embayments, the birth and death of sea ice govern the fortunes of entire ecosystems. In early winter, Brazil ice crystals coalesce into nelas, a thin, elastic film that flexes beneath wind-driven waves. As temperatures drop further, this transforms into young ice and, eventually, thick, multi-year flows. The pace of this transformation shapes habitat for organisms from the microscopic to the immense brine channels within young ice host bacteria that feed on organic detritus, while seals and penguins exploit breathing holes in the fast ice until the platform gives way. Scientists establish time-lapse cameras at rookery sites to document the timing of sea ice breakup and formation, correlating these signals with breeding success and juvenile survival rates in species such as emperor and Adelie penguins. Benthic ecologists, venturing from icebreakers in small submersibles, discover communities anchored to the seabed in water depths beyond sunlight's reach. Glass sponges grow for centuries, their intricate silica skeletons forming the backbone of underwater reefs that support brittle stars, amphipods, and polychaete worms. Genetic analyses of specimens collected from these reefs reveal high levels of endemisma, testament to isolation by vast expanses of ice and cold. In some fjords, hydrothermal springs inject mineral-rich fluids that nourish chemosynthetic bacteria, creating localized oases where life thrives independent of surface photosynthesis. Meanwhile, atmospheric scientists at stations like Mawson and Davis monitor the descent and ascent of the ozone hole with ultraviolet spectrometers, balloon zones, and ground-based LIDAR. Year after year, they chart the springtime recovery of ozone concentrations, hopes buoyed by the success of global emission reductions, yet tempered by the occasional deep vortex that prolongs the hole's presence. They also measure trace gas fluxes, detecting minute increases in nitrous oxide and methane transported from lower latitudes. By integrating these data into global atmospheric models, they refine predictions of ozone layer dynamics and its interplay with climate forcing. Geologists, too, contribute to the tapestry of understanding. In exposed Nunatak ranges, where ancient rocks pierce through the ice, they study metamorphic suites and igneous intrusions that record the continent's tectonic past. Samples dated by radiometric methods reveal episodes of mountain building, rifting, and continental drift spanning hundreds of millions of years. These rock records, compared with seismic profiles beneath the ice, validate reconstructions of Gondwana's breakup and illuminate why East Antarctica's cratonic core remains so stable, even as West Antarctica churns with geothermal activity. Education and outreach programs amplify these discoveries, bringing the continent's story to classrooms via virtual reality expeditions and interactive data portals. Students manipulate 3D models of ice shelf geometry, simulate buoyancy-driven circulation under floating ice, and analyze real-time weather station feeds from remote field camps. Such immersive experiences foster a new generation of researchers and policymakers who appreciate Antarctica not as a distant wilderness, but as a keystone in Earth's interconnected systems. In the silent expanse where ice meets sea, the narrative continues to unfold. Each calving event joins the drift of bergs into the Southern Ocean. Each melt season reshapes the interface between water and ice. Each ecological census refines our picture of life's resilience. And beneath it all, the planet's pulse geothermal, glacial, and biological beats on, carrying forward a saga written in ice, water, and time. As we listen, we come to realize that this farthest frontier is not merely a backdrop for scientific inquiry, but a living testament to Earth's capacity for both change and endurance. Along the shifting frontier, where East Antarctica's vast ice sheet meets the Southern Ocean, the secluded region of Shackleton Coast unfolds in pale monotones. Here, the Denman Glacier's immense tongue flows into the sea, past rocky promontories and grounding points where ice fastens to outcrops of bedrock. Subtle gradients at these pinning points create zones of compression, visible on the surface as swirls of deep blue ice and longitudinal crevasses. Scientists aboard icebreakers anchor moorings seaward of the grounding line, measuring water temperatures and currents that surge beneath the floating ice. These measurements reveal how slight increases in ocean heat can undermine the glacier's stability, thinning its base by meters each year and potentially releasing a pulse of ice that would ripple through the coastlines far beyond Antarctica. Not far away, the Mawson Glacier carves a channel through the Transantarctic Mountains, its flow guided by valleys polished by successive glacial epochs. Here, Field teams mount radar antennas on sled-mounted tractors, sweeping the ice shelf and mapping hidden suture lines where tributaries converge. Radargrams show layers disturbed by intermittent surges episodes when the glacier briefly accelerates before slowing, again offering clues to past dynamic behaviors under differing climate states. Ice sheet modelers incorporate these insights into simulations that explore how tributary interactions might amplify future responses to warming, testing whether cascading tributary collapse could reshape entire sectors of the East Antarctic margin. Above the coastal ice, the coastal ranges of Victoria Land stand sentinel against the sky. The dry valleys Taylor, Wright, and Victoria remain snow-free oases in one of the harshest deserts on Earth. Here, polar winds scour every snowflake, exposing gravel plains streaked with sediment transported by ephemeral melt streams. In these valleys, perennially frozen lakes hide beneath translucent ice lids, their dark waters sustained by geothermal flux and seasonal melt. Researchers drill through these capacious lids to lower instruments that record temperature, salinity, and microbial activity in subice waters. In Lake Bonny, divergent layers of saline and freshwater stratify in permanent cross-sections, creating habitats for algae that photosynthesize under filtered light, and for bacteria that metabolize sulfur compounds released from the underlying sediments. On the margins of these lakes, cryptoendolithic communities inhabit fissures in bright sandstone, their pigmented cells absorbing ultraviolet radiation and extracting moisture from fleeting humidity. Molecular analyses reveal unique adaptations, enzymes that stabilize proteins amid freeze-thaw cycles, and pigments that quench harmful free radicals unleashed by intense sunlight reflecting off ice. These biological refugia, confined to microscopic niches, testify to life's capacity to exploit the narrowest of habitats and provide analogs for astrobiological studies of Mars's harsh landscapes. At sea, straddling the boundary between pack ice and open waters, the Ross Sea's polynyas bustle with life. Icebreakers deploy acoustic Doppler current profilers beneath the mobile ice to capture the formation of dense shelf water, which sinks and flows northward as Antarctic bottom water. These current cores transport not only frigid water, but also carbon and dissolved oxygen into the abyss, ventilating the deep ocean and regulating global biogeochemical cycles. In spring, when the polynyas open to sunlight, phytoplankton blooms erupt along fracture lines, drawing in krill and small fish that feed whales, seals, and birds. Oceanographers sample these blooms with towed nets and automated fluorometers, profiling particle dispersion and rates of primary production that cascade through marine food webs. Above, satellite constellations in sun-synchronous orbits deliver high-resolution imagery of ice dynamics. Synthetic aperture radar pierces polar darkness and cloud cover, tracing fractures thousands of kilometers long and capturing the subtle glide of ice at flow speeds of meters per day. Optical sensors capture albedo changes as dust and impurities deposit on the surface, reducing reflectivity and accelerating melt. Data streams from these remote platforms feed machine learning pipelines that flag anomalies merging rifts, unseasonal snow losses, or unexpected accelerations, alerting field teams to investigate before events escalate into irreversible changes. In parallel, the human story of Shackleton Coast unfolds in the legacy of early explorers. Sir Ernest Shackleton's Nimrod expedition first glimpsed these cliffs and glaciers in 1908, naming Cape Roberts and Mount Erebus after familiar landmarks. Today, marine archaeologists survey wrecks preserved in icy waters, such as the remains of supply vessels trapped in pack ice, their decaying hulls now habitats for sponges and anemones. Underwater photogrammetry reconstructs these relics in three-dimensional detail, intertwining narratives of endurance, loss, and scientific discovery. International collaboration remains the lifeblood of Antarctic research. At nearby Scott Base and McMurdo Station, teams from New Zealand, the United States, Italy, and South Korea coordinate logistics, sharing ice runways, laboratories, and research vessels. Joint projects under the Scientific Committee on Antarctic Research probe atmospheric circulation, genetics of krill populations, and geochemistry of volcanic emissions from Mount Erebus. Data sharing agreements ensure that findings from ice core chronologies to ocean temperature profiles feed into global assessments such as the Intergovernmental Panel on Climate Change reports, guiding policy decisions on emissions, ecosystem management, and climate adaptation. Despite these collective efforts, the future of Shackleton Coast and its neighboring sectors remains uncertain. Most models agree that moderate emission scenarios will produce localized warming of up to 2 degrees Celsius by 2100, with corresponding increases in ocean heat content. Under such conditions, numerical projections suggest that parts of Denman and Mawson could begin retreating inland, contributing several centimeters to global sea level rise. International task forces now evaluate geoengineering possibilities, floating shields to dampen ocean waves at grounding lines or artificial pinning points to slow ice discharge. Yet these proposals wrestle with ethical, ecological, and legal implications under the Antarctic Treaty System's mandate of non-interference. In the quiet interstice between ice and ocean, the land-ice-sea continuum pulses with complexity. Rifts form and grow, currents erode and sculpt, ecosystems ripple with seasonal energy, and human curiosity strives to chart the contours of change. Each measurement, each dive beneath the ice, each sample returned from subglacial water adds texture to a narrative that spans geological eons and human lifetimes alike. And as the Southern Ocean's currents lap against the base of Shackleton Coast, the story of Antarctica continues an unbroken epic of ice and sea, of hidden life and ancient rock, of exploration past and futures, yet unwritten. Farther east, along the coast of East Antarctica, the Aurora subglacial basin lies concealed beneath nearly 2 kilometers of ice, its hidden depths resembling an inverted mountain range punctuated by deep troughs. Here, an intricate network of subglacial channels mapped by airborne radar conveys water from the high interior toward grounding zones at the coast. In summer, as surface meltwater percolates through crevasses and moulins, it augments this basal flow, lubricating the ice sheet's foundation and modulating the speed of downstream ice streams. GPS stakes anchored in the ice record's seasonal accelerations of tens of meters per year, while borehole thermistors reveal basal temperatures hovering at the melting point. Together, these measurements indicate that even minimal increases in surface melting, once thought negligible in East Antarctica, can propagate downward to stimulate basal motion, with potential consequences for ice discharge. Above this hidden realm, the surface of the ice sheet bears witness to the passage of eons. Sastrugi wind-carved ridges of hardened snow span the landscape like ripples on a frozen sea, their orientations aligned with prevailing katabatic winds that descend from the Polar Plateau. Automated ground vehicles equipped with LiDAR and ultrasonic sensors traverse these sculpted fields, collecting high-resolution digital terrain models that document snow accumulation and erosion patterns. By comparing repeat surveys, researchers quantify drift rates and snow redistribution, providing essential inputs to mass balance models that assess how snowfall variability affects the ice sheet's net gain or loss. In the skies overhead, remote sensing satellites in low Earth orbit implement multi-instrument payloads to monitor the basin's dynamics. Synthetic aperture radar systems capture ice velocity fields irrespective of daylight or weather, while laser altimeters chart changes in surface elevation to millimeter accuracy. Gravimetric satellites detect minute variations in Earth's gravity field, pinpointing mass changes where ice thickens or thins. Data assimilation frameworks integrate these disparate observations, producing time-evolving models of the basin's health. Is it gaining mass through increased snowfall? Or is it losing mass via accelerated flow and basal melting? Early indications suggest a delicate balance, one that could tip toward mass loss under sustained atmospheric warming. The marine frontier, adjacent to the Aurora Basin, hosts its own array of phenomena. Polynyas form where offshore winds and currents prevent ice formation, creating open water zones even in the depths of winter. Here, buoyant sea ice is constantly created and advected away, drawing surface water into wind-driven circulations that concentrate nutrients and fuel phytoplankton blooms come spring. Autonomous floats drift within these polynyas, sampling temperature, salinity, and dissolved oxygen. Their data reveal that brine rejection during ice formation drives dense water formation, which then sinks to supply Antarctic bottom water, a key component of the global overturning circulation. Changes in polynya area and intensity, driven by shifts in wind patterns and sea ice cover, thus have ramifications reaching far beyond local ecosystems. Ecologists studying the marine margin deploy remotely operated vehicles, ROVs, in summer months to film the underside of fast ice and the seabed beneath. In these twilight habitats, filter feeders such as sponges and bryozoans blanket the substrate, while amphipods and isopods dart among their branches. Each video transect adds to a growing database of species richness and community structure, allowing researchers to track how biological assemblages shift in response to environmental change. In years when polynyas open earlier or persist longer, biomass measurements indicate elevated productivity that cascades upward through krill to support greater numbers of seals and seabirds. Overhead, seabirds like Antarctic petrels exploit fast ice edges as hunting grounds, scanning the water for fish and krill beneath a canopy of ice. GPS-enabled tags on these birds record flight paths spanning hundreds of kilometers, linking foraging behavior to sea ice extent and ocean temperature anomalies. Analyses show that in years of reduced sea ice cover, petrels travel farther and expend more energy to locate prey, with implications for breeding success and chick survival. These behavioral responses serve as living indicators of change at the ice-ocean interface. Meanwhile, glaciologists continue to probe the basin's secrets through targeted drilling campaigns. Hot water drills bore through the ice to install subglacial observatories that record seismicity, water pressure, and electrical conductivity. Seismic tremors reveal stick-slip motion as the ice slides over bedrock irregularities, while pressure sensors capture the ebb and flow of subglacial water, correlating with meltwater inputs from above. Electrical conductivity probes infer sediment concentrations, evidence of basal erosion that supplies fine rock flour to the ice stream bed, in turn influencing friction and flow. These interdisciplinary observations form the backbone of predictive models, seeking to determine whether the Aurora subglacial basin will remain a stable reservoir of ancient ice or transition toward a more dynamic, less predictable state. Northward of the Aurora Basin, the expansive Shackleton ice shelf extends seaward in a broad arc, its floating front buttressed by pinning points where grounded ice rises from the seabed. The shelf's stability hinges on these anchor points. Where they erode or disintegrate, the ice shelf's capacity to resist inland flow diminishes. Recent multi-beam sonar surveys map the sub-ice shelf bathymetry, revealing deep troughs carved by past glacial surges and smaller ridges that once supported short-lived advances. In areas where the shelf rests on these ridges, basal melt rates are minimal. Elsewhere, where it floats free above deep waters, warm circumpolar currents funnel in, thinning the shelf at several meters per year. To monitor these processes, a network of moorings lies beneath the ice shelf, each equipped with temperature and salinity sensors, current meters, and upward-looking sonar to track underside morphology. Autonomous underwater vehicles, AUVs, are periodically deployed through boreholes to map the underside directly, photographing melting features, marine life, and sediment deposits. Analysis of these images shows that melt channels align with tidal currents, scouring the ice into fluted shapes and depositing sediments in downstream cavities. These melt features evolve seasonally. In winter, colder water slows melt and allows marine ice-fresh water refrozen onto the shelf underside accumulate in depressions, while in summer, warmer currents reverse the pattern, deepening channels and weakening the structure. On the surface, GPS stations anchored near the grounding line detect horizontal movements as the shelf flexes under tidal loading. Tilt meters record vertical oscillations, and broadband seismometers capture microseismic noise generated by crack propagation. In tandem, satellite interferometric radar tracks calving events, small rifts that propagate over weeks before releasing tabular bergs hundreds of meters across. By cataloging these events, researchers assess how seasonal heating, ocean currents, and shelf geometry interact to determine fracture trajectories and calving rates, critical factors in modeling future shelf evolution. Marine biologists focusing on the shelf edge document how ice scorisbergs driven by winds and currents reshapes benthic communities. ROV surveys compare species composition in scour-dominated zones to more protected troughs, finding that hardy echinoderms and sponges recolonize scoured areas within years, while slower-growing corals require decades to reestablish. These observations inform theories of disturbance and recovery in polar benthos, revealing that even in cold, nutrient-poor waters, life's cycles of destruction and renewal persist. In the skies above, meteorological stations monitor air temperature, wind speed, and humidity, feeding data to regional climate models that simulate interactions between atmospheric circulation and ice shelf surface melt. During summer, melt ponds form in depressions on the shelf, absorbing solar energy and draining through hydrofractures that can deepen pre-existing cracks. High-resolution drones survey these pond networks, generating orthomosaic maps that guide models of melt-induced fracturing. The convergence of meltwater processes with dynamic ocean forcing underscores that ice shelf stability depends on simultaneous control of both variables, a challenge for forecasting in a warming world. Meanwhile, seismic reflection profiles through the ice shelf have imaged glacial layering and ancient grounding zone features wedges of sediment deposited during past stillstands. These buried signatures record episodes when the ice shelf advanced or retreated, framing its current behavior within a longer history of natural variability. Cross-referencing these signals with ice core chronologies and marine sediment records enables reconstruction of shelf fluctuations over the past several millennia, offering analogs for potential future shifts. Onshore, the landscape transitions from ice to raw rock at the shelf's landward margin. Here, glacial moraines, ridges of boulders and cobbles mark former positions of the shelf grounding line, while raised beaches indicate past sea levels influenced by isostatic rebound. Geologists map these features to constrain uplift rates, combining cosmogenic nuclide dating with GPS measurements to determine how quickly the crust recovers as ice loads change. These insights refine models of post-glacial rebound, critical for interpreting modern sea level records and predicting coastal responses worldwide. At research stations near the ice shelf perimeter, scientists collaborate on cross-disciplinary studies. Glaciologists, oceanographers, and biologists share field camps and lab facilities, integrating ice, water, and life observations. Environmental protocols ensure minimal disturbance, with waste removed and fuel stored on raised platforms to prevent contamination. Such integrated operations exemplify the Antarctic Treaty's ethos, fostering partnerships that transcend national boundaries and disciplinary silos. Farther offshore, icebergs calved from the Shackleton ice shelf drift into the Southern Ocean, their trajectories tracked by satellite and by drifting buoys that relay oceanographic data. These bergs, some the size of small islands, transport fresh water and sediments as they melt, influencing local stratification and nutrient distributions. Ecologists aboard research vessels sample waters downstream of bergs to assess how meltwater plumes stimulate plankton growth, revealing that even individual bergs can create hotspots of productivity in the otherwise sparse Southern Ocean. Thus, from sub-ice shelf currents to floating ice islands, the continent's rhythms manifest in interconnected cycles. The stability of the Shackleton ice shelf, shaped by bed topography and ocean currents, governs the flow of inland ice. Ice shelf changes modulate marine habitats and global circulation, and calved bergs seed biological oases before dissolving into the vastness. In this tapestry of ice, water, rock, and life, every process weaves into the grand story of Antarctica's past, present, and unfolding future. Beneath the shimmering halo of satellite beacons that circle endlessly overhead, Antarctica's story turns inexorably toward its future, one shaped by the interplay of warming climates, advancing technologies, and shifting human priorities. Along the fringes where ice meets open sea, observer networks of GPS, radar, and tide gauges now relay live data to research centers, enabling near-instant detection of glacial acceleration or ice shelf flexure. In remote corners once accessible only by months-long traverse, autonomous floaters slip beneath thinning ice shelves, logging temperature and salinity changes that presage basal melt. The continent's pulse has become measurable in real time. Its responses to atmospheric and oceanic forcing laid bare for analysis and, perhaps, intervention. Yet even as the tools of science grow more sophisticated, the central drama remains the same. Will Antarctica's immense reservoirs of ice hold fast or yield to a warming world? Climate models converge on a spectrum of possibilities. Under high-emission pathways, projections suggest that by 2100 West Antarctica could lose tens of centimeters of equivalent sea level rise, with a risk of tipping points leading to multi-meter contributions over subsequent centuries. In contrast, if global temperatures stabilize within 1.5 degrees Celsius of pre-industrial levels, the continent's mass balance may shift only modestly, accumulation from increased snowfall, nearly offsetting enhanced basal melting. The key hinges on how rapidly ocean waters around the continent warm and whether sub-ice currents accelerate melt beneath the great floating shelves. Conservationists and policymakers, armed with these projections, debate strategies for safeguarding both the ice and the living communities that depend upon it. The Commission for the Conservation of Antarctic Marine Living Resources has proposed expansion of no-take zones, protecting critical krill habitats that underpin the entire food web. In parallel, the Antarctic Treaty consultative parties explore measures to limit shipping activity in sensitive regions, minimizing risks of fuel spills and noise pollution that could disrupt marine life. At the same time, technological innovators pilot renewable energy, microgrids, fields of modular solar arrays, and wind harvesting turbines designed to operate through polar night, and gaily aimed at reducing station diesel consumption and cutting the research footprint. Geoengineering concepts, once relegated to theory, gain cautious attention. Proposals range from deploying underwater berms to block warm currents from ice shelf cavities, to seeding reflective aerosols in the lower stratosphere to offset solar heating. Each idea faces scientific, ethical, and legal hurdles. Could interfering with Antarctic currents destabilize remote ecosystems? Would stratospheric injections risk unforeseen climatic side effects? And how would such interventions comply with the treaty's principles of non-interference and environmental stewardship? As workshops convene, scientists underscore that mitigation at source of rapid global decarbonization remains the most reliable strategy to preserve Antarctica's integrity. Meanwhile, the continent itself adapts to new roles. Virtual reality expeditions and live-streamed aurora cams bring Antarctic vistas into homes and classrooms, spurring a broader public invested in its fate. In universities worldwide, students analyze real-time data feeds, modeling ice sheet responses and ecological shifts, honing the next generation of polar scientists At sea, eco-certified tour operators partner with researchers, offering passengers hands-on citizen science experiences from plankton.net to ice core demonstration, fostering personal connections that translate into advocacy for polar protection. And yet, amid all this forward momentum, the timeless rhythms of Antarctica endure. Ice continues its slow march toward the sea. Subglacial lakes pulse and settle, and in hidden pools beneath kilometers of ice, microbial life persists in its chemical solitude. Emperor penguins circle parent to chick on creaking floes. Krill emerge in spring's first light, and the wind still sculpts sastrugi across endless plains. The southern lights unfurl, auroral curtains dancing above grounded stations, reminding those who watch that our planet remains a living, breathing system whose southernmost reaches reflect both fragility and resilience. In this unfolding chapter, Antarctica stands at a crossroads, its future shaped by the choices humanity makes today. Will it be a testament to our capacity for restraint and cooperation, a preserved haven of science and wonder? Or will it become an emblem of lost thresholds, its vast ice reduced, its ecosystems altered beyond recognition? As researchers decode the signals woven into ice cores and drifting bergs, as policymakers negotiate protections, and as individuals around the globe raise their voices, the southern continent's next act is still being written, one that beckons each of us to listen, learn, and act on behalf of Earth's quietest, most profound epic. In the remote sweep of East Antarctica's coastline, beyond the familiar reaches of the Ross and Weddell Seas, lies the Whitmore Mountains Regiona, labyrinth of Nunatak ridges and hidden valleys that thrust through the ice like islands in an alabaster ocean. Here, exploratory teams on specialized snow tractors traverse sastrugi fields under pale sun, their instruments logging subtle variations in ice thickness and surface roughness. The ridges themselves, composed of billion-year-old metamorphic and igneous rocks, bear witness to tectonic upheavals that predate even the assembly of Gondwana. Exposed crags reveal glacial striations, parallel gouges, carved by ancient ice streams now vanished, while sheltered alcoves host pockets of wind-blown dust, their petaled patterns in the snow hinting at prevailing katabatic currents. Beneath this rocky coda, airborne radar surveys have mapped a complex series of subglacial basins and ridges, some hundreds of meters below sea level, forming a secret topography that directs meltwater flow toward the coast. During austral summer, surface melting on sun-facing slopes percolates into the firn, feeding slender moulins that connect to basal channels. Sensors deployed deep within these boreholes record pulses of water pressure each time warm air incursions elevate surface melt, causing transient accelerations in the overlying ice. These pulses, though measured in centimeters per hour, illuminate an intimate feedback loop between atmosphere and ice. A fleeting warm spell on the plateau can set off a cascade of basal lubrication that propagates downstream, hastening ice stream velocities kilometers away. On the frozen seaward edge, where the Lambert Glacier feeds the Amory ice shelf, ground teams have stitched together a network of GPS stations and time-lapse cameras to chronicle crevasse formation and rift propagation. Here, the ice flows with a quiet majesty, its surface marked by gently curving flow stripes that trace the glacier's path from interior heights to the ocean. In winter, low sun angles drape these stripes in soft violet shadows, accentuating the subtle undulations of the ice road. When spring's light returns, meltwater ponds appear in depressions, their cobalt hues absorbing heat and carving new drainage channels that sometimes cut directly through the ice shelf in spectacular hydrofractures. Each new fissure tells of the shelf's resilience and fragility, a record of seasonal extremes that may foreshadow longer-term retreat if warming trends intensify. Ecologically, the Amory Front is a hotspot of under-ice productivity. Submersible vehicles, guided through boreholes, have discovered curtains of brine-enriched water swirling beneath the shelf's lip, nourishing dense mats of ice algae and communities of filter feeders draped beneath pendant ice arches. Video transects reveal sponges and bryozoans thriving on the ceiling, their delicate forms sculpted by currents that feed them with organic detritus from surface blooms. Each borehole sample brings back microorganisms hitherto unknown to science: psychrophilic bacteria that metabolize iron and sulfur compounds, hinting at biogeochemical pathways untapped in warmer waters. These hidden ecosystems challenge our notions of where life can persist, blurring the lines between ocean and ice in a realm of near-complete darkness. Above, the polar sky unfolds in a theater of subtle color. During the brief dawn and dusk of austral summer, the horizon brightens to blush pink and soft orange, a muted glow that seeps across the ice plain in gradual diffusion. When the sun dips below the ridgeline, a violet afterglow lingers, casting everything in a dreamlike palette that lingers long after human vision has dimmed. In those moments, the world feels suspended between timescales: ancient geology, slow ice flow, and the ephemeral spark of life beneath the shelf. It is a place where the boundaries of perception stretch, inviting contemplation of Earth's hidden architectures and the unseen forces that sculpt them. Far to the south, toward the continent's geographic pole, the transpolar drift and the Amundsen sea low conspire to shape the climate of the interior ice cap. Atmospheric models now capture how synoptic storms, born in the Southern Ocean, funnel cold, dry air along pressure gradients into the heart of Antarctica. These polar incursions carve troughs of low pressure that accelerate katabatic outflows, deepening sastrugi fields, and redistributing snow in patterns that only the most sophisticated LiDAR surveys can resolve. Researchers deploy drifting weather buoys tethered to the ice surface. Their barometric and humidity sensors feed real-time data into numerical weather prediction models, refining forecasts of cold air advection and snowfall events that ultimately govern the ice sheet's mass balance. In parallel, oceanographers studying the circumpolar current system have unveiled a hidden influence: internal Rossby and Kelvin waves that propagate along the continental slope, modulating the intrusion of warm circumpolar deep water onto the shelf margins. Moorings equipped with temperature, salinity, and pressure meters, anchored along transects from the slope to the grounding lines, record periodic warm pulses mere tenths of a degree above freezing, that linger long enough to elevate basal melt rates on vulnerable ice shelf undersides. These heat anomalies, though small, integrate over months to produce meters of thinning, weakening the buttress effect that stabilizes upstream glaciers. The interplay of oceanic waves and ice stability emerges as a critical coupling in Antarctic dynamics, one that demands integrated models, bridging scales from kilometers to planetary circulation. At the summit of the Polar Plateau, cosmic physicists monitor high-energy particles raining down through the ice sheet. Arrays of neutron detectors and muon telescopes spread across the snowfield capture showers of secondary particles that reveal the composition of cosmic rays. These data not only inform astrophysical theories about supernova remnants, but also offer indirect insight into solar variability and thus into one of the many drivers of Antarctic climate. In this union of astrophysics and glaciology, Antarctica becomes a scientific nexus, a place where cosmic phenomena and terrestrial processes intersect, each echoing in the other's records. As the planet warms, the fate of this polar bulwark hangs in a delicate balance. Ice sheet model ensembles project that by mid-century, interior snowfall may increase by a few percent, marginally augmenting mass in the highest domes even as coastal ice losses intensify. Yet the net outcome remains negative under most scenarios, with coastal thinning outpacing gains inland, yielding global sea level rise measured in tens of centimeters by 2100. The greatest uncertainties center on tipping points thresholds, at which ice stream acceleration or shelf collapse becomes self-sustaining. To narrow these uncertainties, international teams now pursue ambitious borehole campaigns that deploy fiber optic cables for distributed temperature sensing, seismic arrays to track basal slip, and pressure transducers to monitor subglacial hydrology in unprecedented detail. In the end, Antarctica's story is still being written, its pages turned by snowflakes and melt droplets that conspire to reshape a continent. Every sensor deployed, every core drilled, and every data assimilation system launched brings us closer to grasping the full tapestry of interactions from cosmic rays to subglacial rivers, from microbial niches to continental-scale ice flows. And as the ice drifts, fractures, and reforms, so too does our understanding evolve via testament to human curiosity and the enduring mystery of Earth's final frontier. In the deep winter stillness, when the sun no longer graces Antarctica's horizon, the continent's silence is broken only by the distant rumble of ice quakes, subtle groan as glaciers adjust to ever-shifting stresses. Seismometers buried beneath snow register low-frequency tremors from subglacial stick-slip events, tracing an underground ballet of ice sliding over bedrock asperities. These tremors, often too faint for human ears, reveal zones of basal thaw where meltwater lubricates the glacier base, permitting sudden shifts that ripple through the ice sheet. By cataloging thousands of such events, glaciologists map the boundaries of fast-flow corridors, those hidden arteries of ice that feed great outlet glaciers toward the coast. Above these subterranean motions, the surface transforms under the grip of cold air drainage. Katabatic winds funnel dense, frigid air from the high plateau downslope corridors, gaining speed as they descend and carving elongated dunes called sastrugi into the snow. For field teams traversing this landscape by snow tractor, these ridges pose a challenge. Each bump and trough alters the vehicle's momentum, requiring constant navigation adjustments. Yet the sastrugi themselves are records of wind patterns, their orientations shifting over seasons in response to changes in large-scale pressure systems. Automated LiDAR stations measure their growth and decay, feeding data into climate models that seek to link atmospheric variability with snow redistribution, and ultimately with the mass balance of the ice sheet. Scattered across the plateau, autonomous weather observatories endure the polar night, powered by thermal generators and wind turbines designed to operate without maintenance for months. They record temperature inversions so stable that layers of air remain stratified for days, trapping cold near the surface, while slightly warmer air flows aloft. These inversions influence surface energy balance by suppressing turbulent mixing, allowing radiative cooling to plummet temperatures to record lows. Balloon-borne sondes, released during brief weather windows, profile these layers in fine detail. Their data crucial for validating regional climate models that predict how plateau temperatures will respond to global warming. Hidden beneath even this ice and wind regime lies another world of mystery. Vast networks of subglacial lakes interconnected by ephemeral channels. During winter, pressure from snow and ice forces water to migrate through porous, still and narrow conduits, filling some lakes while draining others. Geophysical surveys detect deflation and inflation of the ice surface by centimeters as lakes empty and refill, a cycle that recurs over years or decades. Each lake may host microbial ecosystems sustained by chemical energy from oxidizing iron and sulfur, dissolved from bedrock or by the slow decay of ancient organic material buried in sediments. As scientists lower sterilized probes into boreholes, they anticipate discovering novel life forms, organisms that have persisted in isolation for millennia, their metabolisms tuned to eternal darkness and crushing pressure. Yet even in winter's heart, life finds a foothold. Antarctic mid-destiny flightless insects emerge from patches of moss and lichen, surviving on nunataks that punctuate the ice sheet. Despite temperatures that rarely rise above freezing, these hardy invertebrates glide across damp rock when humidity permits, feeding on microbial films. Their existence in these oases, sustained by geothermal warmth and occasional meltwater seeps, underscores the tenacity of life in niches carved by geological heat and atmospheric quirks. As spring's faint glow returns to the southern sky, a new chapter begins in Antarctica's annual cycle. Melt begins at lower elevations, where solar angles climb above the horizon, coaxing fragile trickles of water down wind-swept slopes. These melt streams carve transient channels in the firn, pooling in shallow depressions to form ephemeral lakes that shimmer like glass under pale sunlight. Scientists monitor these features by high-resolution satellite imagery and drones, tracking their expansion and drainage. When water accumulates in sufficient volume, it drains catastrophically through hydrofractures, vertical shafts that propagate cracks deep into the ice shelf, sometimes precipitating calving events that reshape coastal geometries. In coastal zones, the drama unfolds beneath floating ice shelves. Tidal flexure pries at pre-existing weaknesses, while warm circumpolar deep water intrudes in slender plumes along the seabed, melting the ice shelf space at its grounding line. Submersible gliders, equipped with temperature and salinity sensors, thread through narrow fractures to map these under-ice currents, revealing pockets of accelerated melt where ice meets ocean head-on. Their data feed into coupled ice-ocean models, refining predictions of how rapidly ice shelves may thin and fracture under sustained ocean warming and how soon the inland glaciers they buttress might surge toward the sea. When meltwater reaches the grounding zone, it not only lubricates the ice space, but also delivers nutrients and microbial life into the subice environment. Researchers sampling these exchanges find bursts of phytoplankton downstream of shelf cavities, indicating that basal melt can fertilize surface water sand, unexpected twist-linking ice sheet dynamics to marine productivity. In turn, krill swarms follow these blooms, drawing in whales whose migrations trace the oscillations of food availability. Satellite tags on humpback and minke whales reveal nuanced foraging strategies, informed by the shifting mosaic of ice and open water along the continent's edge. Meanwhile, at air conditioning temperatures above the ice, giant petrels and squaws shadow research ships, seizing opportunities to scavenge krill-rich, churned waters. Camera-equipped drones film their aerial acrobatics moments of life and death, played out beneath cliffs of ice and rock. Ecologists use AI algorithms to count bird populations from these aerial surveys, correlating nest density with sea ice duration and prey abundance. Their findings illustrate the tight coupling between glaciological processes and apex predator behaviors, reminding us that changes in ice regimes reverberate through the entire ecosystem. Above it all, the Antarctic sky paints a final flourish each evening. The aurora australis, rippling curtains of green and violet that dance to the tune of solar windbursts. All around, instruments record the spectral signatures of these light's inputs to ionospheric models that connect solar activity to Earth's upper atmosphere. In that shimmering display, ancient processes intersect with modern measurements, and the planet's northern cousin, the aurora borealis, finds its southern counterpart, a cosmic coda, to Antarctica's unending symphony of ice, life, and light. Beneath the dreaming white of East Antarctica, where the sun circles low on the horizon even in summer, lies the hidden network of subglacial waterways that feed the frozen continent's great ice streams. In regions like the Recovery Basin, airborne radar surveys have unveiled branching channels hundreds of meters wide, their sinuous courses cutting through bedrock etched by ancient rivers. In summer months, when slight surface melting on the plateau percolates downward, water pulses through the fern into these conduits, momentarily increasing basal pressures. GPS stakes installed on the overlying ice register subtle accelerations mere centimeters per day. Yet these fluctuations cumulatively affect the timing and speed of massive ice pulses that journey toward the Ross ice shelf hundreds of kilometers downstream. At portable camps on the basin's surface, scientists drill narrow boreholes to instrument the subglacial terrain. Lowered into these holes are pressure transducers that log diurnal cycles of meltwater flux and seismometers that record the faint rumblings of water-driven icequakes as basal channels open and close. Chemical samplers capture water samples that hint at rock-water interactions, revealing iron and silica concentrations that betray the geology of the bed below. When analyzed, these chemistries divulge weathering processes hidden beneath kilometers of ice processes that, though slow, contribute nutrients to downstream ecosystems once discharged at grounding lines. Farther inland, the simple act of snowfall becomes a complex ballet of atmospheric dynamics. Researchers stationed at remote automatic weather observatories measure isotopic ratios in precipitation ratios of heavy to light water molecules that serve as thermometers of past temperatures. By correlating these signals with synoptic charts of the Amundsen Sea low and the Pacific-South American teleconnection pattern, they reconstruct episodes when warm oceanic air intruded far southward, briefly uplifting temperatures on the plateau by several degrees Celsius. Such events, though fleeting, leave lasting marks in the snowpack's isotopic archive, connecting polar climate to ocean atmosphere oscillations thousands of kilometers away. On the coast, tide gauges anchored on steel pilings record the ebb and flow of polynyas-persistent open water areas where wind and current sweep ice away as fast as it forms. In the Cosmonaut and Mertz polynyas, these gauges reveal not only tidal amplitudes, but also longer period sea level anomalies tied to oceanic Rossby waves. These waves, traveling along the continental shelf's edge, subtly modulate sea surface height and influence the influx of warm water masses into ice shelf cavities. Coupled with moored ADCPs, acoustic Doppler current profilers, the data portray a dynamic picture. Oceanographic pulses that, although moderate in temperature, deliver sustained basal melt beneath floating ice tongues. Above this interplay of ice and ocean, the atmosphere conveys signals of change. Unmanned aerial systems crisscross coastal cliffs and crevasse fields, mapping stress fractures in painstaking detail. Their LiDAR surveys detect millimeter-scale displacements in ice shelf surfaces, capturing crevasse opening rates that predict impending calving events. Simultaneously, high-altitude balloons loft instruments into the stratosphere to measure ozone concentrations and volcanic aerosol layers, remnants of distant eruptions that dim sunlight and cool the surface by fractions of a degree. These stratospheric inputs, though small, affect surface energy balances and thus influence seasonal melt onset by modifying the solar radiation reaching the ice. Ultimately, the story of East Antarctica's hidden networks recombines into a narrative of interconnected systems. Meltwater pulses, triggered by ephemeral surface warmth, travel through ancient subglacial arteries, modulating the speed of ice rivers. Oceanic waves, imperceptible to the eye, deliver heat beneath floating shelves, weakening the buttressing ice. Atmospheric oscillations carry warmth and moisture across hemispheric distances, etching their signatures into the snow's molecular structure. Each process resonates with the others in a vast symphonion played out in silent cold beneath the endless southern skies. In the vast expanse of West Antarctica, the dynamic theater of the Amundsen Sea embayment takes center Stygia region, where ocean, ice, and atmosphere converge in dramatic interplay. Here, the Thwaites and Pine Island glaciers, often deemed harbingers of instability, are monitored by networks of GPS receivers, borehole thermistors, and oceanographic moorings. Data relayed in near real time to analysis centers reveal episodic accelerations of the glacier front, its grounding line pulling back as warm Atlantic-derived waters intrude beneath the floating ice shelf. These migrations, measured in kilometers over mere years, underscore the vulnerability of marine-based sectors where bedrock lies below sea level. Field teams aboard the research vessel IB Nanook deploy CTD rosettes into deep troughs carved by past glacial advances, mapping temperature, salinity, and nutrient profiles that delineate the intrusion paths of circumpolar deep water. Simultaneously, AUV's autonomous underwater vehicles navigate beneath the ice shelf's underside, their sonar and camera arrays mapping basal channel systems where melting concentrates. Observations reveal that melt rates can exceed 4 meters per year near grounding lines, thinning the ice until stresses exceed fracture thresholds and calving ensues. Each calving event, inferred from seismic swarms and satellite radar imagery, reshapes the shelf front and alters glacial discharge dynamics upstream. Above the glaciers, airborne radar and laser altimetry flights crisscross at regular intervals, capturing surface elevation changes with centimeter precision. These repeat surveys identify zones of surface lowering, where accelerated glacier flow stretches and thins the ice. Paired with interferometric synthetic aperture radar, INSAR time series, the measurements paint a composite map of ice velocity gradients, revealing tributaries that feed the main glaciers like veins to an artery. Analysts integrate these maps into ice sheet models that simulate future behavior under a range of warming scenarios, assessing whether observed trends portend irreversible retreat or could stabilize if ocean temperatures plateau. In the sky, balloon-borne instruments sample aerosol loading and trace gas concentrations above the ice. Concentrations of black carbon soot deposited from distant wildfire sere measured in situ and compared to snow pit observations. When embedded in the snow surface, these dark particles reduce albedo, increasing solar absorption and hastening surface melt. The quantified impact of this impurity forcing informs energy balance models that predict melt, season onset, and intensity, linking distant anthropogenic emissions to processes at Earth's coldest frontier. On the periphery of fast ice, biological teams deploy ROVs beneath sea ice pans to study under-ice ecosystems. In the dark underbelly of multi-year flows, clusters of sessile invertebrate sponges, hydroids, and bryozoans cling to the ice's underside, filtering detrital particles carried upward by currents. Video transects show how community composition shifts with seasonal meltwater influx, which pulses nutrients into the coastal seas. Genetic sampling uncovers cryptic species, some endemic to the Amundsen embayment's unique niches, suggesting that biological diversity here is higher than previously thought, despite extreme conditions. Communities of emperor penguins, breeding on sea ice platforms adjacent to glacier fronts, confront the dual threats of elevated iceberg scouring and changing sea ice phenology. Biologists tag individuals with satellite transmitters to track foraging routes, finding that shifts in pack ice extent force longer trips to reach krill-rich feeding grounds. Satellite-based thermal imagery of chick-rearing colonies quantifies breeding success in relation to sea ice stability, linking ecological outcomes to glaciological and oceanographic changes in a region of rapid transformation. Back at station camps on remote noon attacks overlooking the embayment, scientists calibrate unmanned snow drones and automated seismic stations that record basal tremors. These tremor low-frequency events, caused by rapid slip at the ice-rock interface, illuminate subglacial hydrological pulses tied to surface melt inputs. By correlating tremor rate with summer meltwater production, researchers infer the efficiency of subglacial drainage networks and their role in modulating glacier speed. The result is a tightly coupled understanding: warm waters thinning ice shelves above, surface melting lubricating glacier bases, and dynamic ice flow delivering fresh water to southern seas. Thus, at the nexus of West Antarctica's embayment, every element from ocean waves and atmospheric soot to hidden hydrological networks and feeding penguins participates in an intricate dance of thaw and flow. Observations across disciplines coalesce into a unified narrative, one of susceptibility to small heat imbalances, feedbacks that amplify ice loss, and ecological consequences that ripple from microscopic algae to apex predators. As this region continues to evolve under climate change, it stands as both alarm and inspiration, demonstrating the interdependence of Earth systems and the imperative of understanding them before the next act of this grand Antarctic epic unfolds. In the drifting expanse south of the Amory ice shelf, where shifting snow dunes pattern the icy plain, lies the sprawling Prince Charles Mountain Sand island of rock crowned by ice, rising above the frozen whiteness like a phantom archipelago. Here, geologists and glaciologists converge to study both the exposed bedrock and the ice that cloaks its shoulders. Deep within sediment-filled valleys carved by prehistoric rivers, fossils of Glossopteris and other Permian flora testify to a time when this land lay closer to the equator, cloaked in temperate forests rather than polar chill. Today, ice cores drilled near Mount Menzies capture volcanic ash layers from eruptions that echoed around Gondwana, their tephra grains embedded in annual snowfall, linking Antarctic records to distant volcanic arcs. Above, the ice surface records the slow march of time in subtle waves. Radargrams reveal glacial reflector layers of ice deposited under past climatic regime, stilted and folded by the slow deformation as the sheet converges toward the margin. In some sections, twisting folds hint at ancient surges, episodes when ice accelerated under increased basal lubrication. Scientists mount ground-penetrating radar antennas on sleds, traversing the plateau to map these hidden structures. By interpreting the reflector geometry, they reconstruct past flow patterns, revealing that even the seemingly static heart of Antarctica pulses with episodic change. At the coast, the Princess Elizabeth Land margin hosts a chain of smaller ice shelves, the West, Shackleton, and Fisherwich Buttress tributary glaciers that drain the high plateau. Recent airborne surveys show that ocean temperatures at depth here have warmed by up to 0.5 degrees Celsius over the past 2 decades, eroding the undersides of these shelves at rates previously unseen. In the summer melt season, hotspots of basal thinning appear where eddies of warm water swirl, identified by thermal loggers mounted on mooring arrays and by CTD casts from passing research vessels. In response, rifts have propagated inland, extending crevasse fields and forcing surface meltwater into hydrofractures that amplify shelf weakening. Marine biologists exploring the under-ice ecosystems in these embayments have used ROVs to film extraordinary communities clinging to the shelf undersides. Brachiopods, barnacles, and anemones cluster in crevices, their long stalks catching detritus drifting in the currents. Genetic analyses reveal unique lineage of species, genetically distinct from those in the Ross and Weddell seas, suggesting long-term isolation by regional oceanography and ice shelf geometry. Seasonal sampling shows that phytodetritus pulses, derived from surface blooms, flow through sub-ice channels to fuel these communities, linking open ocean productivity to hidden habitats beneath hundreds of meters of ice. Meanwhile, satellite altimetry and gravimetry missions continue to refine our picture of mass balance. High-resolution laser measurements detect localized areas of surface lowering where satellite radar indicates accelerated flow. Gravimetric inversions pinpoint mass loss hotspots, corroborating field observations of basal thinning. Data assimilation frameworks integrate these streams, producing near real-time maps of change that guide both scientific expeditions and policy decisions. When anomalies exceed thresholds, alerts trigger targeted airborne or ship-based missions to validate findings and adjust predictive models. On the plateau above, researchers deploy autonomous weather stations linked via Iridium satellite to share hourly updates on temperature, wind, and accumulation. In one networked experiment, snow depth sensors feed data to a drifting buoy that transmits sea ice thickness measurements to ends of a polar continuum connected in an integrated monitoring system. These coupled observations reveal how winter accumulation in the interior correlates with summer ablation at the margins, offering a holistic view of the continent's mass cycle. In the skies above, long-duration balloons carry instruments into the stratosphere to sample ozone and trace gases, while UAVs map surface features and melt ponds with centimeter-scale resolution. The convergence of remote sensing and in-situ observation underscores a new paradigm: Antarctica as a connected system, where rock, ice, ocean, atmosphere, and life blend in an intricate dance. Each data point, from fossil pollen in sediment traps to seismic tremors beneath the grounding line, enriches our understanding of a continent both ancient and ever-changing, a place where the interplay of forces shapes not only its own fate, but that of the global climate and every coastline around the planet. As the sun circles lower and the austral winter draws near, the Antarctic narrative shifts once more into the domain of endurance and anticipation. Research stations brace for months of darkness, winterized to withstand temperatures plunging below 80 degrees Celsius. Generators switch to low-power modes, pipelines are drained to prevent freeze, and supplies are rationed to last until the first flight windows open. Inside, winter crews no more than a few dozen at the largest stations rotate scientific duties with maintenance, exercise, and communal rituals. Movie nights in the mess hall, readings of expedition logs, and occasional telescopic observations of the night sky, where constellations unfamiliar to most are revealed in crisp clarity. Meanwhile, the frozen continent continues its silent symphony of change. Tide gauges register the subtle flexure of ice shelves under lunar and solar tides. Microseismic arrays capture the crackling of crevasse propagation, and distributed temperature-sensing fibers record basal refreezing events when cold conditions clamp down on meltwater conduits. In subglacial lakes like Vostok, sampling probes remain idling in boreholes, ready to resume operation when spring's warmth allows retrieval of conserved samples, a trove of microbial ecosystems, undisturbed for millions of years. Above, the polar vortex strengthens, isolating Antarctic air from mid-latitude influences, deepening stratospheric cold, and sharpening the ozone hole's edge. Ground-based LiDARs continue to monitor ozone depletion and recovery, recording each cycle's variations as evidence of global policy success and as reminders of the fragility of Earth's protective layers. Meanwhile, cosmic ray detectors register seasonal shifts in particle flux, data that help disentangle solar and terrestrial drivers of polar climate. In the ocean, dense Antarctic bottom water continues its descent from polynyas and shelf channels, supplying the abyss with oxygen and sequestering heat. Autonomous floats drift beneath sea ice, profiling the cold, salty currents that snake northward along deep canyons. Their data feed climate models that trace the ocean's role in slow heat uptake, a process that delays but does not eliminate the impact of anthropogenic warming. As winter deepens, life ebbs to its simplest expressions. Microbial communities within cryoconite holes endure in stasis. Tardigrades in moss beds on nunataks suspend their metabolisms. And the great ice sheet, frozen solid, flows only under the weight of geologic time. But beneath this stillness, the forces of heat, pressure, and biology remain vigilant. When spring at last returns, the resurgence of melt, bloom, and dynamism will begin anew, writing the next chapter in a story millennia in the making. And so, as our exploration of Antarctica's depths, histories, and futures concludes, we reflect on a continent that is both refuge and harbinger, a vault of ancient memories, an engine of global climate, and a barometer of planetary health. Its ice holds echoes of past epochs. Its hidden lakes may reveal new life. Its melting edges sound an alarm for all who inhabit the vulnerable shores of our warming world. Yet within its frozen vastness, there is also hope in scientific discovery, in international cooperation, and in the resilience of natural systems. Antarctica's epic endures, inviting us to listen, to learn, and to contribute our own stanzas to the ceaseless verse of Earth's great narrative. As the sun dips below the horizon for another austral night, and the auroras dance their silent ballet overhead, we leave Antarctica's vast expanse with a deeper sense of wonderment, a quiet reminder of our place in this great unfolding story. From forests buried under ice to the secret waters of Lake Vostok, from the courage of Amundsen and Scott to today's scientists drilling deep into ancient cores, Antarctica has taught us about resilience, collaboration, and the fragile threads that connect every corner of our planet. May its silent lessons inspire us to protect this remote wilderness and the delicate balance of Earth itself, so that future generations can continue to listen to the timeless song of ice, wind, and life at the bottom of the world. Good night, and let the echo of Antarctica's endless white guide your dreams.